And good morning, everybody. Thanks for coming back for our final day of our Plant and Soil Conference. And with this first session, we'll be talking about irrigation under drought conditions. So, building on a lot of those topics that we've been covering related to drought over the last few days, and talking about some of the practical on the farm applications that you may be seeing. I am the co-organizer for this session with Michael Kahn, who is the Irrigation and Water Resource Advisor for Monterey County. And our first speaker is Bill Green. He comes from California State University in Fresno, and he is the Advanced Pump Efficiency Program Manager and a Production Ag Education Specialist at the Center for Irrigation Technology. Thank you, Bill.
Thank you. Appreciate you having me today. And it's a pleasure to be here. I will go ahead and share my screen here and get my presentation up. Yes, thank you for having me again today. I'm going to talk about how pumps are being, performance is being put out by drought conditions. There's a lot of issues going on right now. We run the Advanced Pumping Efficiency Program for PG&E here at Fresno State, CIT, and we've got a lot of data that shows what's happening with the groundwater aquifer levels dropping and how that's affecting pumps. So I'm going to go into that. So I'm just going to talk briefly about our program, because if you're worried about this issue, which most pump, especially deep well pump farmers should be, you should maybe think about getting your pumps tested, get the groundwater levels checked, do this periodically to see how that's trending. So the Advanced Pumping Efficiency Program and also Southern California Edison's Hydraulic Services offer these types of programs to help you get your pumps tested. I'll talk briefly about how pumps work and variable versus stable pumping water level conditions. That's kind of what we're talking about. I'll mainly be talking about variable pumping water level conditions today, because that's what's happening with aquifers, and how drought is changing those pumping water levels right now, how that's affecting the pump output. And finally, I want to talk about how every system has a flow and pressure requirement, how that's affected when the pump output is affected. And sometimes we want to bring in that VFDs can assist this. And in fact, I did a workshop recently on variable frequency drives on our webinars for the Advanced Pumping Efficiency Program, and I did live demonstrations of how pumping water levels affect the pump and how VFDs can help with that. And talk about the affinity loss too. Okay, so we offer subsidized pump efficiency tests at APEP. If you're wanting to get your pumps tested and a cost analysis with technical support, this can give you information on your groundwater levels, and essentially will sound the well as part of the test. You can go on our website, pumpefficiency.org, and find out about those. Southern California Edison also, through Hydraulic Services, offers free pump tests. So there's support for you to get your pumps tested. Haven't. We've done about 80,000 pump tests in the last 20 years in our program. So we have tests from all over California. And this is our contact information. This information will be given out later, so I'm not going to spend any time on this right now. Okay, so let's talk about it. First of all, let's just talk about pumps for just a few minutes, a little bit. First off, to understand when it comes to energy and water efficiency, especially energy efficiency, about the efficiency of the pump, we call that overall pumping plant efficiency. A pumping plant is a combination of efficiencies, and you have you have motor efficiency, and you have transmission efficiency, and then you have the bowls and impellers, which are the actual pumping plant itself, and those different efficiencies. You put those all together, and you have overall wire to water, or horsepower in, horsepower out. If you want to look at it, there's different terminologies, pump efficiency. And so, for example, here, let's say we have a 90 on the good OPE that we have there in the middle. We have a 93% motor efficiency and 95 transmission and 76 bowl efficiency. You multiply those all together, and your overall efficiency would be about 67%. And if you put a VFD on that, it'll drop a few more percentage points, because VFDs are about 4% inefficient too. So VFDs, there is inefficiency going through all these different components, and that's why we call it wire to water efficiency. How much electricity or how much energy you're paying for versus how much water is being produced out of that pumping plant. And as opposed to say a poor overall pump efficiency, you might still have 93 motor and 95 transmission, and but your bowl efficiency might drop off to 52%. And then you multiply those together and you have 46%. And again, with a VFD even a little bit lower. And that's what we see occurring quite often with drought conditions right now, because water levels are dropping and it's changing the bowl efficiency. Your motor's probably about the same, your transmission is the same as long as you're maintaining the pumping plant correctly. But we see this happening with drought conditions right now, where efficiencies are dropping off and output of the pump is dropping off too. So that's why this is important. Okay, so one of the important things to understand about pumps, the energy in, or it depends in part on the combination of flow and pressure developed. Pressure we term total dynamic head or total lift. It's the total lift of the pump from the water source. That's why the water source going up or down matters. So that combination of flow and pressure is turned into operating condition, and every pump has a combination of flow and pressure as it operates. However, that doesn't mean that flow and pressure stays the same all the time. It changes, especially with water levels changing. So flow rate we know is flow. We generally measure that in gallons per minute, could be cubic feet per second. It's how many gallons are coming out of that pump discharge in gallons per minute. We always say you should have a flow meter. You know, you got to measure water to manage water. That's one of our favorite sayings around CIT here. And we do workshops on flow meters and accessing that data and using it, and especially with Sigma and irrigated lands regulatory program and nitrogen management plans. All these things, knowing how much water you pump is important. And still, there's a lot of pumps out there in agriculture that do not have flow meters. And even if they had a flow meter that was put in 10, 15 years ago or something, you need to get that checked for accuracy. That's one of the advantages of having a pump tester come by periodically and testing it, because he has his certified equipment and calibrated equipment that they can test versus your flow meter, and you can see how accurate your flow meter is. And this is going to be particularly important when you're having to report this, how much water you're pumping out of the groundwater for Sigma. So very important to have a flow meter. And because of that, and I do workshops on this too, we'll give examples of this sort of thing. I use my own farm sometimes as an example. And just to give a quick point on that, this year I rented a piece next door that was an old flood irrigated field and irrigated through the summer, and didn't have a flow meter on the pump. It was the neighbor's pump and stuff, didn't have a flow meter, and I was doing the best I could to flood irrigate it properly. My drip irrigated vineyard is right next door. Well, when it was all said and done, I got a flow meter. I borrowed a flow meter from PG&E's tool lending library. They have flow meters you can borrow for free, an ultrasonic flow meter. I take it out there and clamped it on just to see at the end of the season how much water I'd been pumping, since I didn't know all season long. I should have done it early in the season rather than late. And I actually put well over 5 acre-feet per acre in that flood irrigated field, as opposed to about 2.5 acre-feet per acre in my drip irrigated field. And yet my vineyard is better vineyard. So I was not very efficient with that water. And that's why it's so important to have a flow meter. I was doing it blind like so many farms do, and they just don't know how much water they're pumping. It's so important to understand how much you are pumping, because you're going to have restrictions on this in the future. So the other thing besides flow rate when it comes to the operating condition of the pump was the total lift or total dynamic head. That's the pumping pressure. And this is just an example here that shows a centrifugal type pump coming out of a reservoir or canal or something like that. But basically, you have the main things you have to measure on that is the suction lift from this case, or if it's a groundwater pump, the lift in feet from the water source as you're pumping. We call that the pumping water level. And then you have an elevation lift, and you have to account for friction losses through the piping and stuff when you're planning your putting your pump in. And also you have to maintain system pressure to run your irrigation system. Maybe it's depending on how much pressure that is. Well, we measure that in feet. So let's say we have a 10-foot suction lift from the water level here to the center line of the pump here. And then let's say we're lifting up a hill 190 feet. Okay, this is not to scale, obviously, but so far we've lifted the water 200 feet. We've calculated on our charts and stuff, and there's equations to do this. Irrigation designers would do this, pump designers. That we're going to lose about 20 pounds pressure from the water here until we get it over to our pressure gauge where our sprinkler system is over here. Well, 20 is not feet, so you have to multiply by the constant 2.31, which equals about 46 feet. It's close enough. that converts pressure to feet. And then the pressure itself to run the system has to be accounted for. And let's say it's 60 PSI times 2.31, 139 feet. It'd actually be 139.3. So you can do it exact if you want. Then you add all these together to get the total lift to your pump. 10 foot of suction lift, 190 foot of elevation lift, 46 feet of friction losses, and 139 feet of pressure and maintenance. In this example, we have 385 feet of total dynamic head out of this pump we need, plus whatever flow rate. Maybe it's 100 gallons a minute, maybe it's 5,000 gallons a minute. It just depends. There's different pumps manufactured for all types of different lifts and flow rates within reason for our irrigation systems. And so this TDH, if you're on the west side of Fresno County, you might be lifting the water from 700 feet or something and then having to create pressure. Where I farm in Fowler, it's about 95 feet pumping water level. And then I have to create about 25 pounds pressure to run my system. So I can add all those things together and get my TDH. Or you can have a pump tester measure it and they'll get the TDH for you after your system is in. Anyway, you have these different numbers, and that's how you determine the total lift of the pump. So you have the flow rate and the pressure or the lift of the pump. So once we know these numbers that we have to do to lift the water from wherever the water source is, and we're talking mainly about groundwater right now, then we have pump curves like this that show us the lift in feet and the flow rate. So on the axis on here, we have the total dynamic head or total lift in feet from 0 to 250 gallons per minute. And on the bottom, we have the flow rate from 0 to 900 gallons per minute. So you can see on our curve here that wherever the flow rate intersects with the total dynamic head, for example, at 500 gallons a minute, here is just under 150 feet, about 145 feet total head. That's the operating condition of this particular pump. And if you needed 700 gallons a minute, over here, but you'll only get 100 feet ahead. So that's less pressure, less lift, more flow. Conversely, over here, say it's 200 gallons a minute, you only get 180 feet or you get 180 feet of lift, which is more pressure, more lift, but less flow. Combination of these two things. And so that's our operating conditions along this curve for this pump. However, when it comes to energy efficiency and as being as efficient as possible, you want to stay on your most efficient point. And every pump has this, and it's called the best efficiency point or sweet spot on the curve, we call it. And this is 80% impeller efficiency right here, which is 500 gallons per minute and 145 feet of lift. You know, this pump, like I said, would pump 700 with 100, but look at your efficiencies dropped off. A different pump would be made to be efficient at that point, not this one. So that's our challenge here, because what happens is as your lifts change, because your water levels change, and that changes where you're at on your pump curve. So for example, let's say we had it dialed in perfectly when we installed this pump a few years ago, but now we've had drought conditions for a few years. Well, chances are then at that point, water levels have moved left on the curve. So maybe now you're only getting 400 gallons a minute, which was about 70% efficiency at this point. So you've dropped efficiency of 10% or more, and you've dropped your flow rate by 20% or so. Well, that could be affecting your irrigation system performance and certainly affects how long you have to run that pump. And this is why it's so important to have a flow meter, because these things can occur from April through August in some places in California when the aquifer levels vary. And particularly right now, what's happens usually is, you know, most pumps are set up just slightly on the right side of the curve, and then you move left, and by the end of the summer, you're still in the most efficient range, and you're still getting adequate flow and pressure out of the pump. But what's happening with drought is now it's moving further left. And even when in the wintertime with these drought conditions, we're not getting back to where we once were. So your pump continuously moves to the left on here. And eventually you have to pull that pump out and replace it with a new pump that'll give you the proper flows and pressures to run your irrigation system. And you can imagine if you require 500 gallons a minute, now you're only getting 200 gallons per minute over here. Not only are you wasting a lot of energy to run that pump, you're having to run it a lot more hours, and you're not running your irrigation system properly. So this is what's occurring. And we see this happening even at a faster rate the last couple of years in California with our pumping water levels dropping, since there are numbers we get when we get our pumps tested. So it's particularly crucial right now. And this is how it's affecting it. Now, if you got lucky and you put it in, and this year we have wet winter, which we started out good in December, but January we had a record December and a record January, unfortunately the opposite direction. So this is not helping us. But if we do get some good rains from now on and the water levels come up a little this year, yeah, you might be pumping a little bit more water and getting a little bit more out of that pump. But over the course of time, we're moving left on our curves, not right. And so this is an issue for most all farmers. So I just wanted to point that out, and that's called a variable or fluctuating water table. It doesn't stay constant all the time. A stable condition would be constant, like out of a reservoir, which only a few feet might change or something like that, or a canal or something like that if you're pumping that way. But in some places, we were having serious overdraft issues, and because of this lack of surface water deliveries, we are moving left on our pump curves. And I also I'd like to mention, when you install your pump, you should always keep your original curve that goes along with that, so that you can evaluate. When you get your pump tested, you can plot on that curve. Well, where am I now? Am I still on this curve, or have I moved left or right on the curve, or what is occurring? And so I always tell everybody, when you install your pump, tell your pump company you want the corresponding pump curve that goes with it. So when you get your pumps tested in subsequent years, that you'll be able to plot against that and see where you're at. So the other thing that happens with pumps too is they wear out and they come off their curve. So there's all kinds of different conditions. We go into those in our workshops all the time, but this is just a quick primer on how you can see what's happening with your pump. And so, and this is a condition that we see constantly. So again, with a variable fluctuating condition, and you can see here, we have a diagram here. That means the water level is changing. In this deep well diagram, here you have your static or standing water level, which is where the water is before you turn the pump on. And then you turn the pump on and water draws down to the pumping water level. And your bowls and impellers are submerged down here in the water. And so when this pumping water level is right here. So if your static water level drops, because there's the drought conditions right now, your pumping water level drops correspondingly pretty much. And so that's an issue that we're seeing right now. Hopefully you have enough submergence that you don't drop down to where you're out of your pump is out of there. You got to pull it out and put it down deeper if that's the case. Hopefully your well's deeper. And so, but this is called a variable or fluctuating condition. Water levels are moving up and down. The pumping water level is moving up and down also. And there's other things that can cause the pumping water level to decrease. Your well screen could be plugging up and other issues too. But mainly we're talking right now about the conditions because of drought. What's occurring? Water levels are dropping, so are pumping water levels. That means you have a greater lift, more lift in feet, more total dynamic head and feet to the surface. That means you'll have less discharge pressure coming out of that pump and less flow rate. When that water level drops, less flow, less pressure comes out of that pump, and that affects your irrigation system performance. So all these different irrigation systems have flow and pressure requirements. And so your pump should have to meet those so that you can hopefully irrigate as efficiently as possible. With flood irrigation, all it means is you can run smaller sets probably, because you can you're not going to get as many rows running at one time if your flow rate's dropping off. But certainly it affects your sprinkler system or your drip system or your center pivot, fan jets, whatever you have, that can be affected. And that's one thing that's important to understand. On all your blocks, you need to know that flow and pressure requirement so that you can make sure that your pump is matching up to it properly. And we always tell everybody, when you get your pumps tested or when you're evaluating them, make sure you're running your system as you normally do during the summertime when you're irrigating, or during whatever season you're irrigating, because you don't want to have a pressure pump, for example, that runs these sprinkler systems open flowing and take a pump test on it. It's not going to show you a true picture of how you're doing with your energy and your flow rates and things like that during the actual irrigation season. Here's a different pump curve. It looks a little bit more, that simple pump curve I showed you earlier is one I made up on my computer. Here's one that actually comes from a manufacturer for a pump variable speed drive or variable frequency drive. And I was going to take just a few minutes to talk about VFDs, how they can help you with your variable conditions and what a lot of growers are doing. As you can see here, we have our total dynamic head and feet on the left, 0 to 140, and then our flow rate 0 to 5,000 gallons per minute along the bottom here. And these different pump curves right here at different RPMs on this pump, because what a variable frequency drive does, or variable speed drive does, is slows the RPMs on the pump shaft. And that changes the flow and pressure output of that pump. also the energy signature too. So a lot of farmers are, because of the very fluctuating water tables, when they have to pull their pump now, they're actually putting in a new pump. If they suspect that they're going to continue to have this issue, they're oversizing their horsepower on their pump so they don't have to pull it out every year. And then they're using a VFD and they slow the pump down to create whatever conditions they actually need. And then as the water levels drop, that pump speeds up to meet that demand so they get the proper flow and pressure out of that system. So for example, here, let's look at these curves here. These numbers here are the efficiency numbers here. It says 50, 60, 70, 75, 80. See how these brown lines, they show how efficiencies drop across the different curves here. So your most efficient point on this pump is running it at a slower speed, 900 RPMs, with about 2,800 gallons a minute, with about 30 feet of total dynamic head. That would be 84% efficient there. That's your most efficient point. However, this whole range in here is relatively efficient. So it gives you a lot of different options, as you see delineated with our letters here, of different flow rates, different operating conditions, different flow rates and different pressures. You could have 4,000 gallons a minute with 50 feet of head, or you could have 3,200 gallons a minute with 80 feet of head, so on and so forth. So it gives you a lot of options here. So if your water level is dropping and your head is going up, your pump speeds up and you just move from maybe this area over here into this area, and you're still relatively efficient, and you're getting the adequate, you stay with the adequate flow rate, or you move straight up and down. Let's say you needed 3,000 gallons a minute here originally, and your water level was 40 feet. Now it's dropped to 60 feet. Well, you'll be pumping right here instead. You'll still be 83% efficient, relatively efficient. If it drops another 20 feet to 80 feet, then you would be pumping in here, and you're still at 80% efficiency with about 3,000 gallons per minute. Now your efficiency starts to drop off, but at least to 75, but at least you're still staying 3,000 gallons per minute. You can run all the way up and down here and maintain your flow rates, even though the feet of head on your lift is changing during those drought conditions. So that can be a great source here of way to do this. Now, the other thing that's good about this is you see the horsepower here. When this pump is at full speed, it's pulling 100 horsepower. However, since you oversized the pump, you know, you didn't need 100 horsepower. When you're pulling your 3,000 gallons a minute with about 40 feet of head right here, you're only pulling about 30 horsepower. And that's where VFDs can save a lot of energy. And that's one of the advantages of them. So if you have a variable fluctuating water table, you oversize your pump, you don't have to pull it out every couple of years. It'll be in there for many, many years, hopefully. And then as water levels change, the pump ramps up and down to meet that demand. And then it does take more horsepower. Anytime you create more pressure or have to lift water farther, it takes more horsepower. That's just a fact of life. But at least you have a range here and you don't have to spend all the money to pull that pump every few years.
Bill, about 2 minutes left.
All right, very good. Thank you. And one thing, and the reason we can save energy that way is called the affinity laws. And if you look right here, if your horsepower was 100 and your top speed on your pump was 1,800 RPMs, if you slowed it to 1,500 RPMs, it's not a straight line savings of energy. That's about 20% less RPMs here, 1,800 to 1,500. It's the difference cubed divided into the original horsepower. So your horsepower afterwards is only 58 horsepower. So the point is, if you slow your pump down and you oversize it and then slow it down, in many cases you'll drop that horsepower much more significantly. It's not, like I said, not a straight line savings on the speed drop. It's because of the affinity laws, there's a greater savings. And so that's why that chart previously showed that if you slow this pump down, like you're at half speed, you're at 15 horsepower now on a 100 horsepower pump. That's all you're pulling. That's where the advantage is. So again, you can reduce water hammer and cavitation, all these things. There's a lot of things, reasons VFDs do a lot of things for you and can maintain your system pressure and flows and all that sort of thing, and properly backflush your system too. And I think that was it for my presentation. If there's any questions, I went pretty fast, but I think I got through in about the right amount of time.
You did. You did perfectly. We're still waiting for some questions to come in, but I really appreciate that explanation of the importance of the VFD and how it, compensates to make sure that you have adequate flow and pressure in the system. I guess I had a question. Would you recommend any other monitoring tools other than a flow meter that might give you an indication? And then also with the flow meter, what frequency would you recommend that managers are monitoring
Okay.
Those.
Well, yes, those are good questions. Yeah, actually, this day and age, with everything's coming into play in my own farm now, I've installed remote monitoring and control equipment, and I've always used a flow meter and stuff. And I think it's becoming more and more important to really dial in your irrigation events and to know what's going on. And that's why I threw the example out of flood irrigated field next door this year, where I did the typical farmer mistake. I was going blind at it. I just made sure I had plenty of water out there, and found out at the end of the year, after I went back and analyzed my data with that flow meter, that I had irrigated way too much. So any of those things are very important, but then you have to utilize those tools too. If you don't pay attention, there's a lot of them installed and nobody looks at. And I think it's really important that you have to utilize those to try to dial in your irrigations as efficiently as possible. If everybody does that, we'll have a lot better luck with Sigma regulations and compliance with them. I'm sorry, what was your second question? I've already forgotten.
That's okay. I was just actually, I could move on to a question in the Q&A, and on that subject of flow meters.
Yes.
Do you know, based on the growers that you work with, what percentage of them use flow meters? And if that number is low, what are the reasons behind that? And then can you talk about some of the incentives that are available for people to install flow meter on their farm?
Well, yeah. First, with the incentives, you have sweep and equip, and then you have all kinds of different incentives that are going out there, and it may become a regular requirement for most of the GSAs for Sigma to be able to have flow meters installed. So I think eventually that's going to be a requirement. As far as how many are out there, when I started this job 20 years ago at CIT, I think they estimated about 10% of agricultural pumps had flow meters installed. And we've improved a lot. I think we're up to 35 or 40% maybe now. That means almost 2/3 still don't know. And I always equate it to driving your car without a speedometer. You don't really know exactly how fast you're going. You can estimate. My wife's car, that's a lot nicer than my old pickup. It's a lot easier to tell, or a lot harder to tell how fast you're going than my vehicle that's bouncing around on the road. So the fact is you should have flow meters, and I think they're within most farmers' budgetary budgets, so that they can install that sort of thing. And if you want to get telemetry, obviously things get more expensive after that. But that's what I would look at there. By the way, you asked me about hertz on this. You should stay, generally the old saying was stay over 30 hertz, and 60 hertz being full speed. So half speed on the pump is kind of the requirement for warranties on VFDs. Although I think some of that's changing lately. Some of the new VFDs can even go a little bit lesser hertz. So anyway, you asked about that. 30 hertz would be about 1/10 the horsepower of 60 hertz, generally speaking. So, I hope I answered that question okay. So.
Yes, well, thank you very much. And there's we're running short on time, but you've got several more questions in the Q&A. If you might be able to answer those, we'd appreciate you getting back to folks. And then maybe at the end of the session, if we have time, I'd like to cover more.
Okay, I will go on the Q&A and check them out. Thank you.
Okay, thank you very much.
You bet, man. Thank you.
Okay. All right. So our next speaker is Allan Fulton, who is a retired soil and irrigation advisor who is based in Tehama County. And when I was a new advisor 5-6 years ago, I had the opportunity to work with Allan for the first few years before he moved on, and I really valued that experience. And so I'm looking forward to hearing from him again and him sharing his knowledge with everybody today. Thank you.
Thank you, May. I hope everybody can hear me fine. It's a privilege to be able to participate this morning. So let's get started on talking about some water management considerations for tree crops under a limited water supply. So I'm going to approach this conversation by suggesting some information and tools that, through my experiences, I think can help manage limited water supplies in orchards. I'm going to kind of take a multidiscipline look at this a little bit, and I'm hoping that what I bring to thought here you will find additive to some of the other good conversations that we've had a chance to be a part of and listen to earlier this week in the conference. In my presentation, I'm going to spend the first half kind of talking about, is there need and to set priorities across the ranch for a limited amount of water when there just simply isn't enough for every orchard to get its ideal amount. And I'm going to spend the second half of the talk speaking to different irrigation system and scheduling tools that might be considered. This is not all inclusive by any stretch of the imagination. We're fortunate when we're faced with tough situations to have a large cache of information and tools to draw from. So I'm going to begin by posing the question, will all orchards respond the same to more water? And I would like to draw from one experience in almonds to suggest to you that the answer is probably not. And so this is some research findings taken from a report, lead author Ken Shackle from UC Davis, but I was also a principal on this project as I provided oversight for irrigation trial in Tehama County. Blake Sandin was also a principal in this study as he provided oversight of a trial location in Kern. And at the time, David Dahl was also a principal investigator overseeing the site at Merced, as was Bruce Lampinen, our statewide extension specialist, providing collaboration. This was a 3-location multi-location trial. We tried to select almond orchards of the same age, approximately same canopy size, tried to start out from the beginning as similar as possible. Now, to make some sense out of this graphic, you need to start at the lower bottom, the x-axis, which is a sum of the seasonal applied irrigation water, the rain that occurred in these orchards after bloom, and the soil moisture depletion that took place from spring to fall. And so if we go to the top graph A, what we have here is the kernel pounds per acre yield response across a range of about 35 to 60 inches of seasonal supplied water. And one of the conclusions that we kind of drew from this particular experience is that despite the wide range in seasonal water use of 35 to 60 inches, we observed a moderate or modest increase in yield at 2 of the 3 orchard sites on the order of about 35 kernel pounds of additional yield per acre for every additional inch of water supplied to the crop. You can see from the slope of the lines up here, the Merced and Kern trials behaved quite similarly. And again, at about 35 pounds per additional inch of water supplied. The Tehama County trial did not respond at all to the additional water. Now, the reason this was described as modest or moderate is as Bruce Lampinen has done other research, and there's been other research trials as well besides Bruce's work, that has suggested that the best almond orchards can actually achieve about 70 kernel pounds of water per inch supplied to the crop. And so, again, that's why we kind of described it as a moderate response. Overall, when we looked at the canopy light interception, these orchards were between 70 and 75% canopy light interception. PAR stands for photosynthetic active radiation, kind of a synonym, if you will. In the case of the Merced and Tehama County trials, our canopy size was larger than you might expect for the yields and for the range of total supplied water. And Kern County was very close to this line. So the conclusion was that it did not appear that growth was a particularly limiting factor at these sites. These trees were growing across that range of applied water. So this caused us to conclude that together these results indicate that other factors besides water stress may be preventing yields from reaching their potential at these sites. Some factors that can confound orchard growth and production responses to water can include a range of horticultural variables as well as other soil and water variables not listed here. In the case of the Tama County trial, the data I just showed you, underperforming rootstock and scion selections and at times poor conditions for pollination were probably factors affecting that yield response to that range of total water. And then there's other possibilities as well as you think about your orchards just across our ranches, from how we manage our light, which may originate with our original tree spacing, our design thinking it was optimal, but then finding out later it was more difficult to grow out the trees and fill that production space. Pruning practices later, either too much pruning off the new fruit wood before it has a chance to really bear fruit, or excess shading that's leading to spur dieback and things like that. Foliar diseases, nutritional diseases, deficiencies, I'm sorry. Second generation orchards in walnuts that are planted back to ground that was previously planted can present an assortment of problems. And then we just have orchards that get to where they're aging out from things like shaker damage and such. So this raises the question, if tree crop production responses to total seasonal water are variable, then how should limited water supplies be used across the farm to maximize productivity and returns? Now, there's a couple options we'll often run across when we are looking for information. And one option is described as a proportional deficit irrigation. This is you just account for your cutback and applied water, and you allocate the water you do have equally across all the mature fruit-bearing orchards on the farm, independent of their production histories. So if you get a 70% allocation, you would cut back. It might be reflected on these orchards by, you would increase your duration between irrigations 30% from what you would normally do, or you might keep your normal frequency, but cut back your applied water 30% each time you irrigate. Again, this is a simpler approach to implement, but it's independent of production histories. Another approach would be to try to prioritize your limited water allocations, allocate enough water to the most productive orchards, and implement cutbacks to the less responsive. And this is going to obviously take more work and be more difficult to implement, but it could be worth it in terms of generating more production and revenue per unit water. I'm going to just say, in terms of young developing orchards, they are not good candidates for water cutbacks during droughts. So they should be high priority. It's important to manage irrigation water to promote tree growth and rapidly develop the fruit-bearing tree canopy in these young orchards. So that's about all I will say about young orchards in the rest of this presentation. So if we wanted to try to come up with some sort of approach to prioritize how we apply our limited water supplies, what is the information and tools we have available to help identify orchards that are more responsive to water from those less responsive? And I think we've got some tools that are readily handy for us and should be helpful for us. You have your orchard production history. Maybe with time, we'll even have better abilities to predict what the current year's yield will be. As been emphasized, I think I can demonstrate to you another angle where measuring your water is important, and if you're not doing it, you should be, for your own best insights. And then I want to show you how thinking about midday canopy light interception, assessing it, can be useful. And then you have, of course, your own familiarity with your orchards, where you may know of other known limitations, say a walnut orchard heavily infested with crown gall, or an almond or walnut orchard that has Botrytis or a phomopsis. Anyway, so one of the things I want to just bring to our attention is, one of the things I would try to to assess is water productivity. And this is usually defined in some unit of water per, or some unit of production per unit water. I think at the farm level, it would be pounds production per acre foot of applied water. Could also use revenue generated per acre foot of applied water. Just a simple example, I have one orchard, a walnut orchard, 4,500 pounds per acre. It, on average, over recent years, has used 3.3 acre feet of applied water. Orchard 2, 6,100 pounds of dry end shell yield, but it gets by with a little less water, 2.9 acre feet. So the water productivity for Orchard 1 would be about 1,364 pounds versus Orchard 2, 2,103 pounds per acre foot. And if I had this knowledge, I would be inclined to give Orchard 2 higher priority to meet its necessary water requirement and possibly consider Orchard 1 as a little bit lower in line for my limited water supply. Another way that we can begin to evaluate and prioritize orchards for their response to water is evaluate midday canopy light interception and its productivity, or said a different way, pounds of crop production for each % of light interception. Now, Bruce Lampinen has done a lot of work on this and presented this type of data in a number of reports, walnut and almond research reports, and it tends to be presented graphically. I tried to take and adapt from those graphic presentations this table. Bruce has suggested that you can expect or describe different yield categories ranging from great to poor, and you can expect different amounts of crop production per unit light interception. In the case of walnut, which is sold and valued as an in-shell product, a great yielding orchard might yield in excess of 88 pounds of walnut per in dry and shell walnut per 1% light interception. Average orchard 50 to 75, and a poor less than 25. Now, almond has a different scale because it is we value it and sell it as a cracked kernel meat, and in a similar light, it's about half that of walnut. So a great yielding orchard would be about 44 pounds per 1% light interception, whereas a poor could be as low as 12.5 pounds per 1% light interception. So I give you this criteria a little bit because orchards with higher crop production per unit canopy light interception are likely to have a higher water productivity. It's a simple calculation. You divide the crop yield that you measure at harvest time by the canopy light interception. Now the challenge is, how do I measure canopy light interception? And so this is the most rudimentary way that I can think of doing it, and that is using digital cameras and doing your own little bit of work, trying to just take pictures in different parts of the orchard and inserting grids with some reasonable scale and try to assess from that midday, the shading midday occurring from about noon to 1:30. This little example, this do-it-yourself example, this represents about 18 squares, and that grid of 44 is shaded, which represents about a 41% midday canopy light interception for a young prune orchard. We can get more sophisticated and certainly get more accurate. The Lampinen Lab with Bruce Lampinen as the lead has developed an iPad and iPhone app that you've probably heard of before. Same idea, you take pictures, but it's more sophisticated and I'm sure more accurate than my do-it-yourself technique at estimating your average PAR, photosynthetic active radiation, which again is essentially midday canopy light interception. Here in this example, about 86% canopy light interception. So it is possible to get at this canopy light measurement with some practical level. Of course, you can turn to aerial imagery. NDVI is closely related to PAR and midday canopy light. We've heard mentioned in other presentations series imaging, which uses a fixed wing application. There are satellite images that are available. I know Crop Manage that UCANR is developing, has been developing for many years, has some ability to link into satellite imageries and estimate canopy fraction. So now I'm going to break away from that angle for a minute, and I just want to say that I think that to back up a previous speaker's point, monitoring groundwater can be very insightful in prioritizing orchards and during limited water supply times. And this can be done manually with a well sounder, as I'm doing here at this pump, or it's something that can actually be automated and measured remotely. And the reason I break from this and suggest this for a minute is it's important to monitor your pumping water levels in relation to your well design, your screen depths or your perforation depths, to know if a well is getting close to being threatening, close to going dry, or also you can use this information to relate to any type of sigma regulation that may occur in your own local water basins. I think the combination of looking at your water productivity, your canopy light assessments, and knowing if you have some wells that are at more risk are some important things that line up whether some orchards are more sustainable in drought than others. Okay, now I'm going to drop to the field level, and I'm just going to only mention one slide that just emphasized that good irrigation system design, steady maintenance, and periodic evaluation of that system just remains important. It will always be. We have a growing data set thanks to the mobile irrigation lab in Tehama County that's been running since about 2000. It has over 1,200 irrigation system evaluations up to this point. Most of these systems are micro irrigation in orchards, and the results suggest that about 1 in 4 or 1 in 5 systems, so 20 to 25% of the irrigation systems have been observed to have less than a 70% distribution uniformity. And that means that in those orchards, there's 25% of the area is getting twice as much water as 25% elsewhere. And so that it would suggest those low DUs are placed to save some water that could be used either later in that orchard or elsewhere on the farm. So now I'm going to dive in here for a minute on measuring tree water status. I think it's an important tool, being a direct indicator of the crop's stress levels and being able to associate those with impacts on tree growth and crop development. I'm not going to get into it deep at all. I know, worked with the pressure chamber plenty of years myself to appreciate the labor intensiveness of it and understand why it's not always appealing. And so I remain hopeful and in the past have worked with automated remote sensors. The sensor on the left is a type of sensor that can directly measure trunk water potential, pretty much very similar to what you would measure with a pressure chamber. The device on the right is a dendrometer that's an indirect measure based on the trunk growth characteristics of the externally from the tree. So these tree water status, I'm hoping, becomes more and more practical to acquire better, more thorough data, the higher frequency data.
5 minutes, Allan.
Of course, okay, I'm going to give it a shot here. Canopy temperature application. So aerial applications obviously would be nice, something that would be quick, give us a field-wide point of view. This is something that Blake Stanton has worked with more than I and has indicated he finds it to be very promising. In my own experiences, this was our almond trial in Tehama County back in 14 to 18, where we had pretty good sized plots, about a half acre each plot, ranging from 74 to 116% ET over those 5 seasons. And we did take occasional flights, and sure enough, through aerial imagery and use of model conductance algorithms, we could pick out these plots. So I'm hopeful for that. I know in our case we experienced some logistic constraints a little bit, but anyway, so I'm not so much emphasizing the specific tool, but just saying that tree water status is an important indicator for us. So I'd like to work towards the end here, share one experience in a walnut orchard that we had to demonstrate the potential value of water status. It's a project funded by the Walnut Board, California. We started in 2014. We took data until 2019. Chandler Paradox. It was in close proximity to the Sacramento River. You can see the details on the planting. It was a deep, well-drained soil. We used tree water status to determine with a pressure chamber and stem water potential to guide when to begin the start of the irrigation season. We had 5 irrigation treatments. We had the grower's typical treatment, which tended to start about 30 days after leaf out, which put us around the end of April. 4 other trigger levels, allowing the trees to reach either 1, 2, 3, or 4 bars drier than the fully irrigated baseline prediction for the specific weather conditions. Each treatment was replicated 5 different times in randomly placed plots. And overall, this was a fairly good size experiment, encompassing about 12.5 acres. This was first year of the results. The grower baseline, you can see the 5 treatments, the approximate irrigation start date. You'll see here on this first year, the same start date for these 2. This is kind of the ballpark start date. We irrigated each plot specifically for its own tree water status, so there was a range in start dates. You can see that in that first year, our applied water ranged from 38 inches to as low as 25 inches. This represented about 100% of ET after you counted the rain that occurred after bloom or after leaf out initiated. And we see that we were as low as 66% of ET. Now this first year, the yields were not very interesting, I guess I'd describe them. First, you'll recognize they were kind of low. This was about a 9-year, 9th leaf, and so we had some hedging interactions going on in there at that time. And we saw kind of no significant difference in yield, but a trend towards lower yield with the more stressed trees, mostly due to smaller nut size. As we continued with the experiment, one of the things I want to point out to you is one of the more interesting things was responses that we saw was that the start dates and everything tended to extend later into the season, even the growers. When he was tended to be irrigating early April or into April, he tended to move more towards early May. And we extended clear out into June and July on some of these irrigations, when in the first year, we were kind of wrapping up by definitely by the end of June. The other thing that changed was the amount of applied water that was applied. This occurred because the grower watched our treatments and felt that at harvest time, our trees looked healthier than his trees did, and they actually did. Those trees that had some stress actually were less stressed at harvest time than the ones that had earlier irrigation. You can see we applied a lot less water. Some really large savings in applied water. Here you can see the yields ranging from 5,360 pounds to 4,940 pounds. Only the 4 bar below baseline was significantly different because of the variability among the plots. One of the things that we saw interesting was towards the 3 and 4 bar below baseline, we actually got a boost in edible yield. And I believe this was probably attributable to the fact that when we delayed irrigation, start of irrigation, it tended to create smaller external nut size, which when we filled the kernel late season, we did a better job of filling the nut and getting a higher edible kernel. When we coupled our yields with relative value, the benefit of this little boost in edible yield, you can see that we were down about between 2 and 6% on relative crop value. And again, this is trying to minimize the impact of drought using tree water status and keeping as much acreage in production and minimizing the impact on each acre. So I'm about to wrap up here. I would like to suggest to you the orchard settings where tree water status is likely to be more effective at reducing irrigation and managing water shortages is in our medium and high rainfall regions, which is the green colors, and even the yellow is 10 to 15 inch, which does reach into the San Joaquin Valley significantly. The deep uniform soils of fine sandy loam texture that allow deeper root development, and orchards that have potential for capillary movement of water upward into the root zone. Situations like rivers or tributary influences, orchards bordered by surface water canals or drains, and non-saline soils and water, and with non-saline soil and water. In essence, the pressure chamber really became effective at helping us identify those orchards that were really experiencing gradual, subtle tree water stress versus those orchards that would be quick and abrupt and steeper levels of water stress. And when it would help us identify those orchards, we could save a lot of water where we might be able to use that on other places on the farm or across different ranches. So I'm going to wrap up. If I was to try to build my toolbox to manage drought, I'd be interested in having real-time crop ET information so that I have a good real-time measure of the upper limit of my irrigation water needs. I definitely want to apply or be able to measure my water. I would suggest taking a look into if practical ways of evaluating midday canopy shading. Use this in combination with your orchard yield histories to make some assessments on water productivity. I do think keeping track of your learning to use, having well-sounding capabilities, measuring water table, and learning to use those and relate those to what you know about your wells is important. Always good irrigation system design, steady maintenance and periodic evaluation of your irrigation system performance. And I do think there's a place for capabilities of monitoring tree water status. And then one topic that has been covered, I did not have time to dig into, but I think it's important for us to understand the stages of tree and crop development and their sensitivities to water stress. So I don't know if I left you any time, but thank you.
We are out of time, Allan. Thank you so much. It's a lot of information to cover in a short amount of time. You do have questions in the Q&A and also in the chat if you could provide some input on those. Thank you.
Okay, thank you.
Okay, our next speaker is Dr. Sharon Bennett. She's a professor of soil science and crop nutrition at Fresno State, and her research focuses on the salinity impacts on crop production. Thank you, Sharon.
So thank you for the opportunity to talk on this challenging topic and salinity management under drought conditions. And we'll jump right in. So unfortunately, there's no magic solution for salinity problems. Really, it comes down to good soil and water and crop management. But I do want to acknowledge that in preparing for this talk, I talked to some of my colleagues who have contributed some nice ideas and insights. Steve Groton, Bob Hutmacher, Michael Kahn, and then I'll be demonstrating some decision support tools developed by Blake Sandin and Lao Shen Wu at UC Riverside. So there is a drought tip that was put together by Michael Kahn and Khalid Bali, and it has some very good information. In the next slide, I'll give you, tell you where you can locate it. But it goes through some of the calculations on leaching, particularly reclamation leaching. So that reference is shown right here. And we also have the Ag Salinity and Drainage Manual, Hansen, Groton, and Fulton. Allan just spoke a few minutes ago, which is a very good resource. And then sort of the one that everyone goes back to is Ayers and Westcott, 1985, FAO 29. That's where the published yield loss threshold values are for salinity tolerance in various crops. That's shown here. And then another resource is FAO 48. So I'm going to try to be very brief on the salinity basics. It's certainly important information, but I'm hoping that this doesn't take up all of the talk and I can emphasize a bit more, talk about leaching, maintenance versus reclamation leaching, decision support tools for salinity management, and demonstrate these two decision support tools. I have a slide at the end. I probably won't have time for it with some of the insights from the individuals I was referring to. And then we'll be asking the question, how to manage salinity under drought conditions and still consider, the risk for nitrogen leaching. So where do salts come from? The parent material of the soil. On our west side, we have more marine sediments, and soils tend to be more enriched in salts, boron, and selenium, as compared to the east side of the valley, where the soils are granitic in origin and generally lower in salts. Certainly irrigation water, those down in the Imperial Valley, the Colorado River water tends to be more saline. On the west side of the San Joaquin Valley, for many years, we had very low salt canal water, but the high volume applied, even though low concentration, turns out to be a large amount of salt that's added to the soil. And then as our water supplies have become reduced, people are using deeper groundwaters, in some cases more saline. And then certainly salts can be contributed from fertilizers, manures, other amendments, perched water tables, a little bit less of a problem now as there was the conversion to micro irrigation. And for those in the coastal areas, sea spray or seawater intrusion. Across all these situations, when we have inadequate drainage and inability to export salt from the San Joaquin Valley, this is what really is the challenge for salinity management. So climate has a very large effect on our soils, and we're in a semi-arid climate. So typically we have neutral to alkaline soils. I like to put this up because not all of those neutral to alkaline soils are salt or sodicity affected, but some of them are affected by salinity, by sodicity, or the combined condition. And I think that all of you have seen this table, just to point out that it's very important to identify what type of soil and really what type of water that you're working with. For this table on soils, you might just have a saline condition, and then basically you have high salinity, you're not affected by sodicity, and leaching is the main tool. Your soil structure is not impacted. When you have sodicity in the picture, in the presence or absence of sodicity, in the presence or absence of salinity, then that's where you have a situation where the soil structure is affected. And then you may be looking at chemical amendments, particularly for the sodic soils, and they also have very high pH. And so you may be looking at pH adjustment. So we can assign these soils a certain classification, but realize over time, the chemical condition of the soil can change, and there can be progression from non-salt affected to some level of salt impact. So I just borrowed this slide from Bob Hutmacher. When do we need to use gypsum or some of our acid amendments? Well, certainly when we have sodicity, when we have a high sodium ratio to the calcium and magnesium, that's typically where we need the gypsum. Sometimes in soils that simply have low infiltration, they may not be affected by sodicity. Gypsum can be a good tool. But if we are just affected by salinity, then we don't need these chemical amendments. And just briefly, I think all of us know salinity effects on plants. Osmotic effects are the more immediate effects. So there we tend to see it's more difficult for the plant to extract water, and we generally see reduced height, as in these celery plants, and reduced leaf size or reduced canopy size in the case of tree crops. And then more slowly over time, the toxic, or we call specific ion effect, generally due to the sodium and chloride. Boron is also a toxic ion, and you can see the leaf damage in these pistachio leaves. Sodicity, the impacts, as I mentioned, are on the soil. The sodium disperses the clays. We have the loss of aggregation. We can have crusting and reduced infiltration. Here you can see in this almond orchard. And it, in this case, is localized. We have some areas where the infiltration is very poor. So obviously we need to address the infiltration problem. And then if we have salinity, we can work with the leaching. Also, if we have that sodic soil and very high pH, then we can have an impact on availability of certain nutrients. And so again, addressing that chemical condition. So I have a long list here of practices needed to manage salt-affected soils. I won't be able to go through all of them, but certainly knowing your irrigation water analysis and whether you have elevated levels of the toxic ions and or boron, soil sampling and analysis, again, diagnosing whether it is saline soil, or do you have those associated conditions of sodicity? And then soil mapping. Proximal sensing with the EM38 can be effective to know whether, do you need to leach the entire field, or are there areas of the field that are more saline or sodic where you can focus your leaching or chemical amendments. I'll focus mostly on the leaching today, discuss reclamation or maintenance. And then for the amendments, again, if you have sodicity, then you want to look at some of this, gypsum or sulfuric acid. If free lime is present, you can use that. And appropriate irrigation management. And lastly, there are, for many crops, varieties or rootstocks that have higher levels of salinity tolerance and can be an effective tool. So leaching, that's the process of applying more water to the soil than the soil can hold, which gives you gravitational flow below the root zone. And the idea is to physically move those salts downward. It is really the key factor in controlling salinity in your root zone. And you can ask the question, well, we're sending salts downward. What about nitrogen? Are we going to leach nitrate? Might we move pesticides downward? Well, the answer is yes, but we would try to optimize our leaching for times when nitrogen levels are low in the soil or other constituents. So the maintenance leaching, that assumes that the level of soil salinity is not excessive. And so it tries to ensure that there's only small changes over time. So you apply sufficient water including extra water, so that those salts don't accumulate. And that's really a proactive approach. You're trying to avoid the accumulation of salinity. And the leaching requirement calculation that I'll be going over refers to the maintenance leaching. And then we could ask the questions, given the current focus on nitrogen management, do we really want to do this maintenance leaching? Do we really have the luxury of doing that? And another important point I'll be making is that possibly we're overestimating the amount of water required for leaching with that traditional leaching requirement calculation. The reclamation leaching, we do allow salinity to accumulate in the root zone, and then end of season or dormant season, or periodically we do some heavier applications to reclaim the soil. And that is more feasible, perhaps, if our irrigation supplies are scarce in the case of drought. So this is the traditional equation for leaching requirement. And I'll just go through a calculation here. And oops, let me get this out of the way. There we go. So it only considers the irrigation water salinity. And the ECE that you see here is actually not your soil salinity, but it's that threshold value based on soil salinity for yield loss in the crop, the Moss-Hoffman salinity tolerance threshold. And so if we take, and we have an irrigation water of 1.4 decisiemens per meter, we would input those values. If we're growing tomatoes, the published yield loss threshold might actually be higher for some of our improved varieties, but the published threshold is 2.5, and we come out with a leaching requirement. Leaching requirement is a number always between 0 and 1 of 0.126, and then on a percentage, it would be 12.6% more water. Then we can use that leaching requirement to calculate what would be the applied water. So we have the ET of the crop, and then we plug in that value of 0.126. And instead of applying 28 inches, the traditional calculation predicts that we would apply 32 inches to maintain that soil at an EC below that threshold value. So again, a very conservative approach, which we may not be able to continue to do. So this is a paper that was published by Sharon et al. In 2005, some work done in Israel and in the United States. And this dominant factor approach is saying that factor is really going to be controlling. So if salinity affects the crop to the extent that ET is reduced, then perhaps just applying the normal crop water requirement, we go back just this 28 inches here. If this is the normal ET under non-saline conditions, but if saline conditions are reducing that ET, maybe we're actually getting some leaching and we don't need to bump up the water application all that much. So this is a figure from that paper, and it's showing two different crops, melon and corn, under non-stress conditions. And this isn't their normal water requirement. It's the potential evapotranspiration. This is based on a Class A pan. And these are pretty high salinities, 9 for these two crops. And that has, under the salt stress condition, the crop is maximizing its yield at only 60% of the normal water requirement. Now, if it wasn't quite so saline, it would maybe need 80% of that water requirement. But again, the yield is being constrained. And so you have less total evapotranspiration. This was a study done by Blake Sandin, Louise Ferguson, and some others with pistachio. They were irrigating with waters of different qualities. And the main point here is that you had significant decreases in the cumulative evapotranspiration under, even at 4 decisiemens per meter. There wasn't yield loss until you got up to the higher salinities, irrigation with 8 and 12 decisiemens per meter, but there was reductions in ET at all these different salinity levels. And the evidence for that, they monitored the soil moisture, I think using neutron probe, and in these non-saline or low salinity, non-saline and low salinity, the soil moisture level was relatively low and they had a hard time keeping up with the crop ET. Under the high salinity treatments, the volumetric water content was 80 to 100% of field capacity for almost the entire season. So by applying the same water in all treatments, they had, in these reduced ET treatments, they had very high soil moisture. This is another study by Julia Marino and Daniele Zakeri, and they had a non-saline orchard, and then within a saline orchard, they had areas of low, medium, and high salinity. And you can see another example how the ET was reduced under these high saline conditions. So we do have some decision support tools that we can use as points of reference, I would say, where we can get some idea of how much leaching would be required. And then under drought conditions, we may not be able to do all that leaching, but have an idea what would be the ideal amount. And so I'll start off, this leaching calculator was developed, I believe, by Blake Sandin. It's on the UCCE Kern County website. And then I'll also show one that was developed down at UC Riverside. It's called Salinity. It's a web-based program. And I'll jump right to that. You can see that here. And so it allows you to input a crop, and then an irrigation water quality, the soil texture. If you don't know the soil texture, this links you out to Toby O'Gene's web soil web, I think it's called. And you can get the soil texture based on the survey, choose your irrigation system, the irrigation efficiency, and then it will calculate the leaching requirement. So I'm going to just go out for 1 minute to that program and just show you that it really does work live. Okay, so here's the almond cumulative ET. This is in millimeter, and irrigation water quality of 2, clay loam soil, drip irrigation. I'm going to put 85% efficiency, and then it'll calculate based on these parameters, site-specific parameters. It'll calculate the leaching requirement by that traditional equation that I showed you, 36%. So that's pretty high if you're going to put on basically a third more water than your normal water requirement. But this program is only recommending 14% because they are taking into account things like the soil texture and also that potential for reduction in ET. So here is the normal water requirement, 1220. And then you can see that with the leaching fraction added in, 195 more millimeters, it goes up to 1415. And then here would be the amount of water to apply if you added in the leaching fraction, as well as accounting for that only 85% irrigation efficiency. And then let's say that you just don't have that amount of water. And so you can't do 14%, but you're going to try to do 5%. Do some kind of leaching. Well, according to this calculator and those published yield loss threshold values by Moss and Hoffman, your yield is now down to 63%. Now, there are improved newer varieties and improved rootstocks where maybe that yield reduction wouldn't be so great. But instead of having the root zone maintained at 1.5 decisemen per meter, you're now at 3.5, and the total amount of water required is, well, it's less because you've chosen a lower leaching fraction. So I'm going to go back to the PowerPoint, but I think this is a useful tool to kind of give you just some idea of what is going to influence in terms of the water quality, the soil texture, the efficiency of the system. And one point of caution here, though, is sometimes if you keep changing things, you may get some output that doesn't make sense. And then you really need to either refresh or just start again and input new values, because sometimes it doesn't seem to update as well as it should. Okay, let me go back to the PowerPoint.
We've got about 5 minutes left, Sharon.
Okay, thank you. So I just, let me go back to full screen here. I just pasted in a couple of additional, this was the almond that I just went through, and example for, all right, an example for tomato, little same irrigation water quality. This is a a little more salt tolerant crop. So 19% by the traditional leaching requirement by the traditional equation. And this program is recommending 7%. And again, if you only have 5%, then it's going to bring down a little bit the total amount of water that you need to apply. 642 if you're just accounting for leaching, or 755. Again, this is millimeter if you're accounting for the irrigation efficiency. Sorry. Okay, and then lettuce, just another example. The program is, the traditional equation is recommending 44% leaching, in part because we have a somewhat saline water for lettuce, and the program is recommending 11%. Okay. So another tool that I just wanted to quickly point out is this Excel-based calculator that is available on the UCCE Kern website. And so I'll just go out to that one for a minute. And this one I think is fairly user-friendly. It has quite a few worksheets in it. I'm just going to focus on this one and possibly one other. So what this one does, it allows you to, here's an example, and then it allows you to put in data for your soil, the saturation percentage, pH, EC, these three, calcium, magnesium, sodium. A lot of times if you get a soil test report back, it's on milliequivalent per liter basis. So it's going to calculate the SAR for you. And then you put in your desired salinity, and then it'll tell you how much water you need to put on, how many inches per foot of root zone to get down to these desired ECs. So up here in this example, here are the salinities for the top foot, second foot, third foot. And I should have highlighted this one, trying to get down to 3 from 5.5, 6.7, 7.3. And you need to apply basically a total of 11.7 inches of water. As a reclamation strategy, you know, that's a foot of water at the end of the season. If you only want to manage the top 2 feet of your root zone, then you would be applying 7.4. There's also a table down here that's based on this graph that you see here. And it provides the required leaching under a reclamation scenario. And there's these 2 different K factors, which is in the numerator here. Denominator is the desired EC over the actual. And I've pasted this into the PowerPoint. If we use, say, that K factor of 0.15, then these are the inches of water per foot of root zone required to, say, in the case of maybe almonds, you got up to 4. You get up to 4 decisiemen per meter ECE. You're trying to get down to 2. You'd have to apply 3.6 inches of water per foot, so per foot of your root zone. And if you were, say, with pistachios, and you had a soil salinity as high as 8, and you wanted to get down to 4, comes out to the same number, but 3.6. If boron is high in the soil, then you generally need to increase that leaching requirement. And you could extrapolate between these 2 values here. Unfortunately, they don't have a lot of different levels, but if you were at 6, this is a linear relationship, you would need to apply 5.4 inches of water per foot depth of soil. Okay, I'll go back to the PowerPoint. And just a couple examples. That calculator also shows you this relationship between irrigation water salinity and what is your resulting soil salinity. Again, theoretical, but based on this table here, if you had an irrigation water salinity of 2, then if you only have 5% leaching requirement, your resulting soil salinity could be 6.3. But if you have that higher leaching requirement, 15%, that you expect to go from an irrigation water salinity of 2 to a soil salinity of 3.2. If you have a high enough leaching fraction, 30%, then you don't expect much change in the soil salinity over your irrigation water. I'm going to skip over this slide, but it was contributed by Bob Hutmacher, some real nice points or comparison between in-season, which is really maintenance leaching, and dormant season reclamation leaching. The dormant season leaching, it has some benefits because it avoids the sort of frequent excess application of water, so less problems with water logging and low oxygen in the root zone. And maybe you can do a better job of choosing to do that leaching at a time when nitrogen is low in the root zone. And by applying a larger volume less often, maybe you can get some of that boron leached. So in summary, with saline soils or saline irrigation, leaching is required. Soil testing, try to do it to assess, how saline is the soil and to what extent you need to leach. Address sodicity if it's a problem, know your water quality. Good idea to monitor soil moisture to get an idea if maybe your ET is being reduced by that salinity. So under water scarcity, perhaps properly timed reclamation leaching might be better in terms of salt and nitrogen management, and certainly conduct that at a time of year when the soil nitrogen is low. And that's it.
Great. Thank you so much. Again, so much information and not enough time, but thank you for wonderful talk, Sharon. And you have some questions in the Q&A. We'll have to move on to a break now. Sharon, if you could please answer those questions between now and the break. I think that the timestamp on your question starts at 9:06. So, okay, we'll be just taking a short break and coming back at 9:35 to cover the session on soil conservation. Thank you.
I guess we will get started with our next session. My name is Sarah Light, and I'm an agronomy advisor with the University of California Cooperative Extension. I am co-organizing this session with Dr. Lauren Hale, who is a scientist at the USDA and a board member with me. Lauren and I first met last year virtually when we were both on a panel about soil health at this meeting. And we were excited to co-organize this one today. Just an introduction to this session, we're going to be talking about soil conservation. We asked 3 speakers. We actually have 4 speakers today because one of our talks has 2 speakers, but we have 3 talks. And we'll be talking about some of the kind of practical and on-farm applications for some of the soil conservation practices, as well as some of the implications of those practices for California around carbon sequestration, green waste recycling, etc. Just as a reminder for those of you who missed our morning intro, if you have questions, please put them into the Q&A, and that will help me keep them organized for our speakers. If you have discussion comments, those can go into the chat, but if you put a question in the chat, it might get missed, and in the Q&A, we can be sure to get that answered either during the talk or afterwards. If you're trying to get CCA credit, there is a QR code that we'll put up at the end, but you can also email the ANR program support group. And if you're trying to get the INMP nitrogen certification credits, that's going to be via email to the ANR program support. So with that, I will go ahead and get started. Our first speaker today is Dr. Jennifer Pett-Ridge at Lawrence Livermore National Laboratory. She has done a lot of work on soil carbon. I recently had the opportunity to see her present at a CDFA panel. She has a lot of knowledge about the opportunities for carbon sequestration in California. In our state, we do have the Healthy Soils program that's been going on, incentivizing these practices. And so from Jennifer, we hope to learn about the opportunities for the actual carbon sequestration. Thank you.
Great. Thanks, Sarah. Thanks. You may see a couple of the same slides that you saw at that other talk. So apologies, but there's some new stuff as well. Let me first just make sure you can see those slides, all right?
Looks perfect. Yep.
Great. Well, thank you so much to Sarah and to Lauren for inviting me As you mentioned, I'm a research scientist at Lawrence Livermore National Lab. I also have an adjunct position at UC Merced. And my group works on understanding the processes in soil that lead to accumulation of carbon. I have a training in microbiology and in isotope tracing. And so we do come at this admittedly from the research perspective, but we are doing more and more work on farm. I would love to be doing more even in California. We've done quite a bit of work with pasture lands in the state, but I will be telling you about both work that we've done in the state and elsewhere, but I think that speaks to the opportunities here. I want to make sure that I give credit to those who actually conducted the work. So these are all folks who were graduate students or postdocs working with myself or with colleagues at our associated universities. And I actually want to give a little shout out to Lauren Hale because she actually helped with some of the data collection that, that I'll be presenting here when she was in a former position. So I'll just start by setting the stage that our agricultural soils across the world have lost an enormous amount of carbon, roughly 500 gigatons of CO2 equivalents. That's not only due to tillage, but a large amount is actually due to erosion. There's actually quite a very interesting study that came out just last week that showed that the Corn Belt of the United States has lost just a huge amount of its A horizon, its organic rich horizon, and most of that due to erosion. So we think of this in a way as a debt that needs to be repaid. And in the United States, we have estimated, we and others have estimated that somewhere between a half to a full gigaton per year could be sequestered in soils. And I'll tell you, I'm focusing most on agricultural soils because those are the ones that we're managing already. So it makes sense to really focus in on those. And so today, what I'll mostly be talking about is the different strategies that I think are worthwhile considering in trying to achieve those kind of goals. So in California, about 2 years ago, I and colleagues at Lawrence Livermore put together an analysis of the carbon dioxide removal strategies that could be used to help the state meet its goal to be carbon neutral by 2045. And to do that, our state needs 125 million tons per year of CO2 removal. And we looked at a lot of different factors, not just soils. We looked at biomass, we looked at direct air capture, we looked at forests, but the cheapest solution, not surprisingly, are what we call the natural solutions. Those would be soils and forests. And we estimated that roughly 25 million tons out of the 125, so 1/5, could come from these so-called natural solutions. And there's definitely integration between them. For example, in our forestry sector, a lot of what we really need to do is removing biomass that might then go into a gasification plant where we not only make hydrogen gas that is potential fuel, but we're creating CO2 that can be stored geologically. But I want to keep it focused on the carbon piece, which is significant and importantly is one of the most economical parts of the picture in terms of the whole state and its calculus of how we can get to carbon neutral. So you're looking there at what we calculated, not surprisingly, is the land that is most amenable to carbon accrual. And that's mostly because it's land that we're already managing, so primarily there in the Central Valley. And we used a tool called the Comet Planner that some of you may be familiar with, which allowed us to look at a series of different conservation management practices, ranging from reduced tillage to cover cropping, conservation rotations, and different kinds of amendments like compost or char. And we looked at how much we thought those could cause net emissions reductions. And so that's the plot you're looking at there. And overall, we're seeing mostly positive values, but I think the main thing I take away from this data and this analysis is the quite large error bars associated with each. We're currently doing a second analysis where we're really digging under the hood of the Comet model to try and get a better handle on those. But this just in a nutshell, points to me at least to say that we really need to focus on doing better quantitative estimates and correlating research that's been conducted already across the state to try and get a better handle on which of these practices do truly lead to significant emissions reductions. So in our new analysis, and this first one was conducted actually for the Microsoft Corporation, who's interested in offsetting some of their historical emissions. We looked again at a lot of the different soil carbon management strategies, but in particular, we included this time deep-rooted perennials. And when we look at an estimate of the how measurable the carbon is, how sure we are that we've removed versus simply just avoided emissions of CO2, the risk of whether we might be accruing carbon in the ground, but at the same time releasing more nitrous oxide or methane, et cetera. There are a number of different metrics. The two strategies that we characterize as being the best are cover cropping and deep-rooted perennials. So I'll talk a little bit more about those in just a minute. Cover cropping, we did an analysis of across the entire US, and the state of California is actually doing quite well. We have many counties that are exceeding 5% within the county using cover cropping. And that suggests that it's an accepted practice and it's moving into a number of different contexts. So we definitely think that that should be encouraged. It has significant benefits in terms of soil carbon accrual and reducing erosion. There are lots of co-benefits that I won't necessarily mention today, but I assume many of you know about. One topic that that often comes up is amendments, and in particular, the addition of compost or different bio wastes. The thing that we find a little worrying in these studies is that the boundaries of the system in terms of analyzing where the carbon came from and how much is accrued are not always drawn accurately. So these plots are meant to show you a number of different metrics. If we think about the amount of carbon that we start with versus essentially a baseline scenario of where that particular soil might have been on a trajectory to go in the coming 5 to 10 years, that's the top line, versus an improved scenario. So if, the baseline is the C sub B, the improved scenario would be C sub I. So we can add an amendment, but not necessarily have a net carbon accrual over the starting amount. If we, when you add that carbon, it actually causes more nitrous oxide loss, or if it causes a priming effect, sometimes we actually get a net loss of the total amount of carbon. So it's really important to think about how much carbon was fixed offsite in that compost or char or whatever bio waste it is that's going to be added. And that needs to be accounted on the new site. We can't just think of those new amendments as a net benefit to the system. We also have unintended and kind of complex effects with no-till. Obviously, this is a topic that's been discussed for quite some time in the context of increasing soil carbon. And if you look at the synthesis of a series of studies above the dashed line, we do see a relatively positive effect, meaning that we're seeing numbers above 0 in a series of studies, but we tend to see those in the upper surface horizons of the soil. And unfortunately, when we go into deeper horizons, going down to up to a meter, we see more of a neutral effect, or even in some of these studies, we're seeing loss of carbon at depth. This can be for many, many reasons. I think the science is still out and still unclear on why. But one of the clearest things that we've seen in many, many studies across the US is that when we use no-till, we tend to increase the amount of greenhouse gas loss. So nitrous oxide and methane emissions frequently go up with no-till. Even though soil carbon is increasing, when you take into account the net balance, we're not always in the positive negative emissions realm. So if I have criticisms about all those techniques, what is my favorite? Well, I'll tell you now. I think that deep roots and deep-rooted perennials in particular are what has got me most excited about the real potential to increase soil carbon storage in our soils. And a lot of this is just based on basic soil formation principles. The majority of carbon below ground comes from roots. And decomposition rates tend to be much, much higher in that rhizosphere zone surrounding roots. We do know that the roots stimulate a bloom of microorganisms, both bacteria and fungi, and those organisms, as they're growing their biomass, they're deriving a lot of carbon from the plant and its photosynthase, but eventually they die. And that so-called necromass can become associated with mineral particles in a way that can last for centuries and even millennia. So that's the process where we think permanent or persistent soil carbon forms. So anything that we do that really stimulates that chain of events, we think has the best chance of increasing soil carbon. Obviously, distributing carbon across a deeper amount of the soil profile, like you see here in these switchgrass roots, these can be many meters deep. That just gives us more opportunity for stabilization to occur. We also in deep soils tend to have less active and lower biomass, microbial biomass communities. So there's less chance of those decomposition processes causing loss. Finally, we've done some meta-analysis of a number of elevated CO2 studies. These have been done in mostly natural systems, but some agricultural systems, and shown that it's grasslands and croplands that really have the most potential to store more carbon, and they store it below ground. So as our climate is warming and as the CO2 concentrations in the atmosphere are increasing, plants are photosynthetically more active. And in grasslands and croplands, that activity is translating to more carbon below ground. In forests, it tends to be more above ground. That's a separate issue. But so that's, again, I think another reason that I think that focusing on grasslands and croplands and roots is really the way to go. And the way that we do that in my lab is we use stable isotopes, mostly of 13 carbon dioxide. So this is carbon that is normally very rare. It's sort of a 1% isotope, but we can purchase a CO2 that's where the 13 has been, is the dominant form of carbon. And when we grow plants in an atmosphere of 13C, we're able to trace that isotope all the way down into the roots, into microbes, and into soil. So that's a lot of the backdrop of the studies I'm going to show you today of how we collect the quantitative data. All right, so I'm just going to give you a few little vignettes on 3 topics. The first being, what are the impacts of roots on soil carbon? And I'm going to start here in a pasture, a California annual grassland. This is up near Hopland, California. And in this situation, we did add a 13 CO2 tracer. We did it in the field in these kind of funky looking chambers you can see there. So the grasses, as they were growing at different times during the spring season, we're taking up that isotope and putting it below ground. That allowed us to trace that carbon over the subsequent several years. And what we did is we partitioned that carbon into a series of different pools, some of them particulate carbon, some of them more mineral associated. The mineral associated carbon is what we think of as having a really, really long longevity. When we measure the age of that carbon with radiocarbon tools, we find it is often thousands of years old. So that's kind of the good place. That's the grave that we really want to see carbon ending up in. So what we found after 2 years of these soils going through their normal cycle after they had been pulse labeled with the isotope is that we were still able to find 23% of the original carbon that had been added. That was a surprisingly large number, that the slug of carbon that was put below ground by those roots and those exudates was still there after 2 years, that a quarter of it was still there. And much of that was associated with minerals. Actually, the mineral component, the carbon just became immediately sorbed onto those minerals. So that's fantastic. It shows there's real capacity of the system to draw in and hang on to more carbon. However, the total amount of carbon in these soils did not change, at least to our ability to measure it. So that suggests that, yes, we're putting a lot in, but at the same time, we must be losing nearly the same amount. So if we can focus on ways where we reduce the amount of that loss, that's obviously the key way to increase. So that leads me to our next study, where we think again about ways we can try to essentially put more in than we're taking out. And in this situation, we're no longer in California. This is actually a field in southern Oklahoma. And here we're looking at a field on the right-hand side of switchgrass. So again, a deep-rooted native perennial, I should be very clear, not native to California, not appropriate for California, but it's grown across a lot of the Midwest and East Coast because it's a potential bioenergy crop. So those roots are going down many meters. On the right, we've got a corn, soy, wheat rotation. So those are only going down several tens of centimeters. And these, both these kinds of managements had been in place for about 10 years. And we went in and we dug deep pits with a geoprobe that you see attached to the truck there. And then we measured the total organic carbon, looking to see how has the carbon in the annual soils, what is the difference between the annual soils and the soils that have the deep-rooted switchgrass? And I think you can just see pretty clearly there in that left-hand plot that in the switchgrass, we are seeing more carbon pretty consistently with depth. We can, in some horizons, get up to twice as much soil carbon, and this is corrected for changes in bulk density. We also, when we look at the radiocarbon age of that soil using 14C analysis, we see that it's younger, which makes sense. The switchgrass roots are drawing young, modern carbon out of the atmosphere, and they're putting it down there in the ground. So that doubling or near doubling of the soil carbon stock is definitely being caused by the impact of those roots. Now, maybe why is that happening? It would be really fun for me, at least, to understand better the mechanism that leads to that phenomenon. Well, our best hint is some analysis we did of what's called EPS, or extracellular polysaccharides. The way I like to think about these is kind of root and microbial glue. They're the biofilm type materials that these organisms make to be able to protect themselves from osmotic changes, from water shocks in the soil. So these organisms make like a little blanket of this gooey glue surrounding their cells. That stuff is great for aggregating soil particles. And we see a strong correlation between the amount of this EPS biofilm glue and the amount of soil aggregation, which again correlates with the amount of total carbon increase. So that right now is our best mechanism that we can think of that is actually what's causing that carbon to stick around for a long time. So now I wanted to say a few words about soil minerals, because just because we're inputting more carbon doesn't necessarily mean it will stay put in all soil contexts. Soil minerals that range from more quartz and phyllosilicate to more clay or ferrihydrate just naturally hang on to different amounts of organic matter. That has to do with their surface chemistry. It has to do with their surface area. I won't go into too much detail on that, but just looking at these images, you can see there are differences in the amount of organic matter that get coated on those surfaces. Now, jumping from this scale to the scale of the entire nation, where if we think about how could we try to pull carbon out of the atmosphere and where could we park it best in terms of the soils of our nation, there are certain sites that have more of the poorly crystalline minerals and clays that are highly weathered that tend to be really good at hanging onto carbon. So any of the locations that you see in this image that are in red or in blue are really ideal for accruing additional carbon, at least predicted by our modeling. So we did some tests to actually try and see how accurate is that modeling. Again, we're using that paired kind of deep-rooted switchgrass annual plot scenario when we went and did a series of surveys across the US in the East and Midwest. And this is a fairly complex plot, so I won't go into too much detail, but I'll just say that the sites where we found more carbon and younger carbon, suggesting that the deep roots were putting it into the ground, tended to be sites that were initially relatively poor in terms of their carbon content. So it's soils that we might call marginal. They often were in the southern US, but sites where we have less carbon to begin with seem to be able to more quickly accrue additional carbon. That's the take-home message there. So then my last topic that I just want to touch on is how we can understand and maybe harness the effects of microbiomes in soil. And when I say microbiome, I'm talking about everything from bacteria to viruses and fungi and even the fauna that form the microbial food web. And all of these organisms are feeding off, the majority are feeding off of root-derived organic carbon. And by managing the types of exudates, the compounds that plants are putting into the soil, we're inherently managing that microbiome, and we can enhance the ability and the availability of water, of nitrogen, of phosphorus, simply by managing that microbiome. Can we maybe also manage the amount of carbon that gets stored? We have some evidence that suggests that the types of exudates that are produced by our deep roots do correlate with the types of organisms that are there. And when we grow plants in a more fertile and a more rich environment with added nitrogen or added N and P fertilizer, we get a different kind of community and a different kind of exudate than if we're looking at a marginal soil context. So that's good evidence to suggest that, yes, these things tend to follow each other. We now are trying to figure out what kinds of organisms would we really want to try to promote? Who are the beneficial partners who we really want more of? And I'll say the one that we know already is our buscular mycorrhizal fungi. We often call these AMF. These fungi partner with almost all land plants, well, not all, actually 80%, and they provide a huge amount of plant nitrogen and phosphorus. We've recently shown they also allow water to move more efficiently to their plant host. And they have benefits in many ways on the amount of soil carbon. And I think a lot of that simply has to do with the massive amount of soil that these fungal hyphae interact with. I know that you've seen these in your soil, and when we did a calculation recently of what is the total length of hyphae in centimeters per centimeter squared, it's something on the order of 100,000 centimeters per centimeter squared of fungal hyphae, as compared to roots, which is about 7. So several orders of magnitude less in terms of the amount of the interactome, the amount of surface area. And you can just, in looking at this SEM of the hyphae, see how much organic matter is sorbed to their surfaces and is being interacting with those fungal hyphae. So again, I think that's a way of helping to move plant carbon out into the soil. And if that's something we can accentuate, then we should definitely do so. So now I'm just going to wrap up, kind of coming back to the state and what I see as opportunities. The first being that soil carbon farming is really still a somewhat nascent idea. You certainly know about the Healthy Soils program. Right now, that's mostly focused on the greenhouse gas emissions. But I think that we need to think beyond just simply our actively managed agricultural landscapes, but also think about some of these, what I call forgotten lands, buffer strips around our fields, strips along highways and railways, brownfields. Even the city of Livermore has recently realized how much turf they were managing. And this is turf that nobody's playing soccer on. This is just chunks of grass that were surrounding their city buildings. And we're now working with them to think about putting in deep-rooted perennials, ideally California natives, that look good, but also might be increasing the soil carbon and the soil health without too much extra maintenance costs. I also think that there certainly are huge benefits that we could have in our managed landscapes on our agricultural lands. There's not currently a program to do a concerted study on this. I would love to see that, particularly in our systems like our orchards and our vineyards, which naturally do have deep roots. I think understanding both the agroecology and the biogeochemistry of how those ecosystems can work to put more carbon in the ground, as well as produce crops above ground, would be just fantastic. And that's something that we've been pushing the legislature to think more about. So just to finish up here, I think that there are real benefits in terms of managing our grasslands and pasture lands for soil carbon, planting perennials, whether that's on forgotten landscapes or in buffer strips. I am in no way suggesting that we turn our annual grasslands back to perennials as they were a couple of thousand years ago, but in the landscapes that we're managing, I think that would be an opportunity. I think encouraging cover cropping, continuing to do that is certainly an enormous benefit and has clear wins for soil carbon. And then it's a little bit more out into the future, but engineering and using some of our genetic tools and our breeding tools to look at creating plant feedstocks, cultivars that have deeper roots, more of that EPS production, more associations with beneficial microbes. I think those can also lead to real benefits for soil carbon. So I'm going to stop there. I'm going to leave you on the slide where I'm thanking lots of colleagues who've contributed to this work, and in particular, the Lawrence Livermore Carbon Initiative that has funded all the analyses that I showed you at the beginning. I'm happy to take a question or two if there's time.
Thank you so much for that excellent presentation. We have 3 questions for you in the chat, but time for only 1 live. So I will read that. And then if you don't mind, your questions in the chat start at 9:46. So you can type in answers and more might come in.
Okay.
But one question that did come in is, what about other nutrients? Are they needed for higher long-term carbon storage? Some work suggests that they do.
Absolutely. There's a good meta-analysis. I don't know the citation off the top of my head. It just came out showing that fertilization does quite reliably lead to increases in soil carbon. However, in most ag settings, it also leads to increases in nitrous oxide loss. So you really have to fine tune that. In most of the settings we've worked in, there we are not doing any fertilization, no nitrogen or phosphorus amendments, and we work in really marginal settings. So it is often still possible to increase carbon without doing amendments of other nutrients.
Thank you. Thank you for that answer. Thanks for answering the other questions in the chat and for your awesome presentation. Really appreciate it. It's my pleasure to move on to our next speakers. We have 2 presenters in the next section, Matt Cotton from Integrated Waste Management Consulting and Neil Edgar from the California Compost Coalition. They're going to be talking about putting compost into context. We have new legislation in California that's in place now that is regulating green waste going into our waste stream and will lead to an influx of compost into the marketplace. And so we wanted some expertise on the context of compost for our California farming systems. So thank you so much, Matt and Neil. I will turn it over to you.
Thank you so much for the opportunity. Neil and I are incredibly thankful for the privilege of listening to that last presentation, which was very inspirational. Really enjoyed that. Really appreciate the opportunity to be here and to increase understanding of compost, which is mostly what we do. These are really interesting times in California, as far as in the state's recently enacted extremely aspirational legislation to divert a lot of food scraps to composting, which is likely to expand production and use. California already consumes about 65% of the urban compost in agriculture, and I think this is going to increase. But we also have opportunities, as we just heard, but possibly with lots of challenges and lots of unknowns, to both reduce the impacts from landfilling a lot of this food, but also in potentially sequestering some of this carbon and all the co-benefits that Jennifer just mentioned. So appreciate the opportunity. This talk sort of came out of a conversation the four of us were having around some ag use, compost ag use workshops. Neil and I and Cole Smith are organizing just to sort of try to get our hands around all that's happening because there's a lot happening in California right now with compost and compost use. Fundamentally, a lot of this is driven by legislation, as it always has been. The most important of these recent bills is SB 1383, which was actually signed by Governor Brown back in 2016. But it really builds on climate change and waste diversion goals of the past 30 years, largely by reducing and better utilizing food waste, whether that's getting it to edible food to people or animals, but really the vast majority of it is going to be talking about getting food waste collected from both residents and businesses, something I often call organic collection for everyone, everywhere, all the time, which is massively aspirational goal. It does include, SB 1383 does include a lot more than just food waste. It certainly has a manure component and some other components, but today we're going to focus a little bit on the food waste given the limited time. But it's got some aspirational goals, including reducing landfill organic waste by 75% in the next couple of years. Obviously, the pandemic slowed a lot of this down. Really hard for jurisdictions to require a restaurant, for example, to implement an expensive new program when they were just trying to hang on and provide all of us food during incredibly challenging circumstances. So while the pandemic sped up many things in society, this legislation is one of the things, or implementation of legislation is certainly one of the things that really slowed down. So none of this is probably going to happen as fast as the Sacramento expected, but it is happening. It is moving forward. Some jurisdictions have been doing a lot of these programs for decades, in some cases in the Bay Area. In other cases, jurisdictions have a lot of work to do to reduce the amount of food waste going to landfill. Largely, this is novel and new because across the country, many states do have ambitious waste diversion goals. This is really the first one that tries to co-manage, if you will, solid waste as well as climate change. There's a tremendous amount of organics currently thrown into landfills, about 24 million tons in 2018. We've been doing yard waste collection in some jurisdictions for decades, but going after food, going after other organics, throwing in some food soil paper, this is relatively new. And adding a food recovery component to get edible food to people and or animals is also very new. That's combining a couple of different spaces. Your typical recycling coordinator is not spending a lot of time talking to the food bank and vice versa. So this bill has already started to build those bridges, which is really exciting. And there's some really great examples of programs around the state of more resources getting dedicated towards food recovery, which of course is preferable to managing these as compost or other sources. But getting into the budget, we had an unprecedented budget surplus. And I've been doing work in and around composting for 30 so years here in California, and we have never invested this kind of money in these types of programs, this level. The Healthy Soils program, is going to get $75 million, which is not exclusively, but largely about, or it's incredibly common to have part of those funds go to adding compost to soils. $5 million for community composting, which is, again, unheard of amount of investment in that. The state has $90 million earmarked for infrastructure grants, which are largely for building new and expanding new composting facilities, new anaerobic digestion facilities. So many observers think we don't have adequate infrastructure to manage the level of organics contemplated by 1383, but we have this amazing resource now to provide some support for developing those facilities. And we do have a robust existing infrastructure at the moment. And again, 10 million for co-digestion, taking food waste in some cases to a wastewater treatment plant, and which helps digest the biosolids as well as creating a gas that can be used as transportation fuel or other things. So an unprecedented time, massive investment at the state level, which does show where the governor's priorities are, where the state's priorities are, and that's a very exciting time. Concurrently, and maybe this is ahead of what I wanted to say for this slide, this is some work I did back in 2019, which seems like about 5 years ago, surveying the largest composters in the state, looking at capacity. And so I documented existing capacity, but also looking at markets and gosh, do we have enough markets for all this compost? Turns out we do. And some of your colleagues at UC Merced have done similar work with a different approach and coming up with numbers on the order of 14 years worth of capacity. So we're doing fine as far as that goes. But concurrent with this massive investment that the state is doing in terms of programs and even infrastructure, this is sort of a golden age for compost research. It's incredibly exciting to see the work. I think it's largely driven by interest in climate change solutions, but I've been in California for 30 years looking at this work. I don't remember a time when there was anywhere close to this much interest in academia towards compost. It's incredibly exciting to try to better understand what we're doing, how it works, why does it work. Incredibly fascinating time. Fundamentally, I've done similar surveys for CalRecycle since 2001, actually. Those were the first to document that agriculture is indeed the largest market for compost in the state. Not surprisingly, when you look at statewide sectors, we have a massive agricultural production. And in this type of soils we have, it's sort of not surprising, really, that agriculture uses up a large share of the compost we make. However, I think it's interesting to realize that was not expected. And there were certainly smart people in the early 90s when we passed similar ambitious legislation to divert waste from landfill that many smart observers thought that mainstream agricultural, conventional agriculture wouldn't accept urban organics. And that's largely been proven false, as these numbers, the share of market that agriculture has taken has increased consistently over the 4 surveys I've done in the past 20 years or so, which is really exciting. And I think there's lots of reasons for that. We still struggle with accessibility. It's a very large state, and compost production tends to have a relationship with population density. So I don't think we're going to have too much compost, which is a complaint I hear a lot. I think we're not going to have enough given all that's going on. If you notice in this pie chart, there's not a single mention of carbon sequestration, which, as Jennifer mentioned, is still fair to say a nascent practice, both in academic science as well as in actual tons going to fields. But the Marin Carbon project back in 2008, sort of a glint in John Wick's eye and others, and has really here in 2020, 2022, there are trucks delivering tons of compost. That's 420 cubic yards going on 12 acres up in the Altamont Hills, sequestering carbon. And we can talk about all the uncertainties, as Jennifer did so eloquently a moment ago. But this is moving real tons, and jurisdictions are looking at this as a way to enhance their procurement responsibilities under 1383, as a way to try to provide some offsetting of greenhouse gas impacts. And it's really interesting that we get all the traditional benefits of adding compost to soil, the carbon increases, the microbial activity, the water holding capacity. And frankly, we could ban all organics from landfill in California just for the water holding capacity benefits, given our constant drought situation here. But we're getting benefits from, diverting these materials from landfills and not creating the methane, the high potential greenhouse gas that you create putting food waste in landfills, as well as the benefits. And the benefits often get shorter shrift, but it's an exciting time that we're moving. We're studying this a lot more. We're looking at it a lot more. We've got a lot more projects going on. There's just all sorts of work being done in California and beyond, and it's an exciting time. So that's what I want to talk about. I'm going to turn it over to my colleague, Mr. Edgar, who's going to give us a little bit more of the nuts and bolts. Neil?
Thanks, Matt. I would add the conversation about compost and this new 1383 requirement essentially is going to double the amount of materials that will be available in the marketplace. So this rapid uptick in the supply of compost really requires a robust effort on behalf of the composters and other folks to help assure the markets that will be available. So while there are considerable available markets, will they be available within reasonable transportation distance from the generators, the producers that are making this material? So talking a little bit about food waste, and that is sort of a new, a bit of a paradigm shift for most of California. There are a number of perceptions about what food waste is and some differing realities. What we're talking about is recovery of food materials that are coming from municipal programs. Most people have some perception that food waste is largely what you see on the left, and that's a collection program that is back of house of a restaurant, vegetative material only. It smells really good. It's like a salad bar. It's just amazing. But a lot of food waste also is the front of house material from fast food restaurants, cafeterias, and other that looks a little bit more like what you see on the right. And a lot of packaging involved in actually recovering some of the food waste that goes along with it. If you're looking at those buckets, difficult to tell whether or not that material is actually compostable packaging, non-compostable packaging. And my group sponsored a bill this last year, which will help clarify identification standards and other standards for compostable packaging, which will help, I think, assure in some ways the quality of the compost that's coming out of these collection programs. Next slide, Matt.
Sorry, I was trying to answer a question. Not paying attention.
Sorry.
There you go. No, go ahead.
So again, food waste in real time, when it's collected by municipal programs, it ends up looking a lot like what you see on the left. It's bagged up and is processed in a variety of ways, some manual sorting, some mechanical sorting, identifying packaging versus the food materials and what you want to process, what you don't want to process is difficult. And a lot of times it comes in bulk. In the screen on the right, you see pallets of product that may be out of code, out of date, may have other production issues which require it to be destroyed. And it's another significant contributor to the food waste quantities and materials that are going to be in the composting stream. Next slide. So in order to address the contamination issue, which is a relevant issue in municipal collection and composting programs, a number of operators, composters, and material recovery facility operators are starting to install depackaging technologies. So this type of a mechanical screen or is equipment that's been adapted from agricultural uses and is very effective in removing the metals, glass, and the plastics. It will tend to pulp up a lot of the fiber materials, depending on the technology, more or less. But there's some current research that is looking at microplastics and whether or not these types of depackaging systems contribute to microplastics, to what level they might be problematic for producing compost out of the material that is processed in this manner. California has a longstanding tradition of organics collection, but it's largely in a residential setting. It's largely green waste collection, yard waste. Most large cities have collection programs historically that started under the previous AB 939, which was our landmark landfill diversion law here in California that was passed in 1989. So during the 90s, these types of collection programs ramped up and are prevalent across the state. Now we're going to look at transitioning those programs to accept yard waste and food scraps. And so it's going to be a training exercise. A behavior change is always difficult, and developing a clear understanding for consumers, residents, and food scrap generators on what goes into what bin, what program, what do programs want to accept may depend upon who their composter is, where they're located, what kind of technologies they use, whether or not paper packaging and food soil paper is a part of that collection is an open question and depends on the service provider. But it's going to be a massive change. Most of the composting infrastructure in California, some 160 out of 200 facilities roughly, are green waste only processors, tend to produce pretty high quality material. So transitioning programs to add food scraps invites contamination issues and changes and a lot of outreach and education to consumers. Along those lines, we've seen tightening food production standards. So the brand owners out there, the restaurants, the grocery chains, and consumers demand higher levels of food production. And we're seeing that play out in real time, and starting in Salinas Valley with the number of foodborne illness issues that have arisen over time, both there and in leafy greens across the Western US and across the country. They have modified their leafy green marketing agreement to reduce the amount of allowable fecal coliforms in biological soil amendments of animal origin. And BSAAOs include, by their estimation, any compost material that includes food scraps. So in a residential program like we talked about, there are roughly maybe 2 to 5% of that material would be food scrap. And out of that, I'm sure it's less than 10% might be meat. But in any event, the perception sometimes is reality. And so whether it's science-based or not, this new order of magnitude reduction in fecal coliform, allowable fecal coliform levels for leafy green production is a sign of the times. And we've seen these type of initiatives spread to other crop types and where there can potentially be more risk. So risk avoidance is becoming a much more prevalent in food production. Contamination is a real challenge. Again, depackaging units help address a portion of it. Almost all the composters that are taking food scraps are both pre-processing materials as they come in and also post-processing of the finished product before it goes out for sale. Again, food scraps are largely being collected in conjunction with compostable packaging in many jurisdictions. Well over 100 jurisdictions in California have mandates on restaurants to include compostable packaging. And now those are somewhat changing to include reusable, recyclable, or compostable. But compostable and food soil paper are a key part of a lot of the organics diversion that we expect to see and invite a host of contamination issues because, again, as I said, the packaging is difficult to discern from the non-compostable materials. And then you're adding glass is another concern in the physical contaminant world. And then you have chemical contaminants that may end up. So some of the paper and fiber packaging contains perfluorinated compounds historically. A lot of those have been phased out and will be eliminated from food packaging by January 1st of 2024 under agreement with the manufacturers. But they're also going to replace those perfluorinated compounds, which act as a grease barrier, help the product perform. Nobody wants to bring home a fiber clamshell full of nachos that is falling apart as they take it out of the bag. So it does have to produce, they do have to produce products that perform, but whether or not those compounds that are replacing perfluorinated materials are additional concern for contaminant remains to be seen. And then there have been historical problems with persistent herbicides, and many composters conduct bioassays, plant assays with the product that they produce, and also test the materials for the presence of those herbicides before they send the material to market.
Neil and Matt, I just want to give you a 2-minute warning.
Okay. So those are issues that face composters on the marketability of their products. Conventional farmers now are largely requiring organic status for the compost that they are willing to accept, which means they're inspected in California. The compost facilities are inspected by the Department of Food and Ag to assure that they are compliant with the National Organic Program. And that is an element of the legislation we passed, that the packaging that is being produced must also meet those National Organic Program standards. Next slide. So again, as Matt said, 2/3 of the compost is sold into agriculture. I tend to believe that the next, if we're going to double the amount of compost produced, that it probably will need to be more than that, 2/3 of the next 4 million tons or so of material being sold into agriculture. 1383 requirements also have local governments buying their compost. So that should be an excellent feedback loop for them on the quality of the material and also help bolster the markets. Climate smart agriculture, technical assistant program have been very helpful in facilitating Healthy Soils Program grants, SWEEP grants, and alternative manure management program grants, all of which are being funded at increasingly high levels. And then a private initiative by a restaurateur in San Francisco, Zero Foodprint, is adding a 1% tax on the bill at the restaurant to help fund the movement of compost and the development of sustainable agriculture that is providing the produce for the restaurant itself, in order to create a circular program where they're providing the funding directly to the grower. Next slide. And as Matt and I have both talked about, compost application is the most dominant practice being funded through the Healthy Soils Program. And I would fully expect that'll continue as more projects are developed in an ever expanding number of crop types and cropping systems.
Thank you so much. This is great. Unfortunately, we are going to have to have the questions answered in the chat. I see that you've already answered one. There's 2 more open questions for you. So if you guys don't mind answering it there. Thank you so much, Matt and Neil, for that very informative presentation. I really appreciate it. And if we have time at the end of the session, we can have more questions. Our last speaker this morning is Dr. May Culumber. She is a colleague of mine at UC Cooperative Extension, as well as on the ASA board. You might recognize her from when she moderated the session earlier today. May is going to be talking about some work she's been doing for several years on predicting the long-term impact of woody biomass application on carbon storage in agricultural soils. May and I are also on the Western Cover Crop Council Southwest Committee together, and we're organizing a cover crop tour in the Sacramento Valley in March if anyone is interested. And I would love to encourage anyone interested in cover cropping to join the Western Cover Crop Council. It's a free membership and you sign up online. So with that, I will turn it over to May. Thank you.
Okay, thanks for the introduction, Sarah. And I have a lot of slides, so I'm just going to jump right into it. But yes, I've been working on this for a few years, and it's just been such a fantastic collaboration. It's on a statewide level between cooperative extension advisors, UC Davis faculty, extension specialists, and USDA ARS scientists. So very successful collaboration that would not be possible if not for all of the staff technicians and researchers, USDA ARS and UCC that have been out there collecting the data. Can't thank you enough for all the work that you've done, contributed to this project. So the California almond industry, as everyone knows, is a pretty large part of California agriculture, and it contributes to our agricultural economy. There's over 1.2 million acres of bearing almonds in California, but estimates are that about 88,000, close to 90,000 acres of those bearing acres are over 20 years old and will be removed in the coming years. And because of the importance of almonds and other permanent tree crops, a lot of these acres are going to be replanted to almonds and pistachios. But it's not the only system. And the next talk this morning is going to be Michelle Leinfelder-Miles. She's going to talk about establishing a bean crop after recycling a walnut orchard. In terms of these orchards that need to be removed, historically, the process for removal was open agricultural burning or taking that biomass to cogeneration plants. So that was the preferred method of disposal, but but in recent years, the majority of burns have become just orchards and vineyards in comparison to other crops historically. And so this is why orchard and vineyards have become the focus of waste disposal alternative methods by the state legislature and the Air Resources Board. And so in 2021, in compliance with the legislator, the CARB mandated the complete near phase out of burning by 2025. And so to help facilitate that effort for growers and landowners, $180 million has gone to the air districts to help facilitate adoption of those processes. And so these are some of those programs that are available. As I mentioned, through the Air Board, you can get up to $600 per acre for orchard and chipping and incorporation, or chipping with an offsite beneficial use, so not incorporating. There's a larger incentive point for orchards that are less than 100 acres in size. So I think it's an additional $100 per acre. And then the Healthy Soils Program, also a source of incentive funds. You can get up to $186 per acre for chipping and incorporation. But those incentive funds max out at $100,000. So as I mentioned, most of this orchard waste has been burned or been used to generate power at cogen plants, but most of those plants have closed and they're no longer accepting waste from orchards. And so with both of these practices, most all of the accumulated biomass carbon is lost as CO2 when they're burned. That carbon source and that biomass could otherwise increase organic matter in the agricultural soils. So whole orchard recycling requires about 5 machines for the process to remove the trees, grind them up, spread them, and incorporate them into the soil. Based on those incentive programs that I mentioned, just since 2018, there's been over 49,000 acres and 1.3 million tons of biomass chipped and incorporated. So in order to understand what the long-term implications are of these large biomass additions, we need to understand the characteristics of the substrate, in our case, wood chips. And then we need to think about, a lot of these lands, as I mentioned, are going to be replanted in ag. So to understand in the presence of the growing climate that we're in, the soils, the trees that are in the ground, in irrigation, fertilizers, tillage, and cover crops, how long will that carbon remain in the ground? And to understand that, we need to think about and study the microbial decomposition processes to understand how will the wood chips make a gradual migration from the chips into increased microbial biomass in the soil and different forms of carbon in different pools in the soil. There could be active carbon pools that are more readily degraded, and then there's those passive carbon pools that tend to bind to soil particles, and that's sort of the source of the carbon that we're looking to see. That's where we get that long-term carbon benefit. A portion of that biomass is going to be lost in the form of emissions and CO2. And so it's very hard to quantify those pools that I mentioned. And there was an earlier question I noticed in the chat, we don't have time, to wait to understand what the long term is. We need to know what the benefit is right now. And so looking at the fluxes of emissions might give us a better idea in a shorter amount of time of what that carbon balance is. And so that's going to be the subject of some of the things I'm going to talk about today. So there have been some whole orchard recycling trials, and the first was initiated by Dr. Brent Holtz, who is a UC advisor in San Joaquin County. He started a trial in 2008. And this was a stone fruit orchard that was incorporated, and it was estimated that this was about a 30 ton per acre allocation into the soil. And this was accomplished with what's called an iron wolf. So it's an old rock crusher. And the picture on the right shows sort of what that, after that process of this thing, it just grinds up entire whole trees and puts them back into the soil, what the size of those wood chunks looked like. So very large pieces of wood. This orchard was replanted to almonds and monitored over time, looking at the soil and the tree performance. And so after about 10 years, Amelie Gaudin, a professor at UC Davis with Imad Jahanazad, who was a postdoc at the time, now he works at CDFA, they did a detailed analysis of what we call this grind and burn trial. And the reason it's called that is because we have the grind from the iron wolf, and it was compared to trees that were just removed, burned in place. So their analysis determined that, and it was very thought to be conservative estimate, that about 8 metric tons per hectare of carbon were retained over the long term compared to that burn wood treatment. And then other soil benefits, they found that sustained higher levels of nitrate, calcium, manganese, iron, magnesium, and boron were higher in those iron wolf treated soils than the burn treatment. And then looking at tree size and yield over time, those orchard recycled trees were consistently higher in yield. Okay, so then you might remember that I mentioned that the process now is looking at all these different machines that chip the material to a much smaller size, and so there needs to be more work done to understand, to predict, what are going to be the long-term consequences for soil organic carbon in the soil over time. But this type of research takes years to complete. I've been working on this for about 5 years, and I feel like there's still so much more that we need to learn. So we can use models to help us predict how orchard recycling might impact carbon storage for a variety of orchard crops of different age and size. And so we're trying to get a lot of that ancillary ground data to better inform those models so that we can get some of this information more quickly, and then we can better quantify on this large scale, large landscape scale, what the benefit is in the short and long term. Okay, so as I mentioned, this current practices produce a much smaller grind size and distribution. The iron wolf just chewed up those trees and put them right back in place in the tree row. The current spreading and incorporation, is total across the landscape. Okay, so we've established several trials throughout the state starting since 2017, and the main goals are to track the changes in carbon storage and overall soil health in replanted orchards in different soil types and different geographic locations. And we're looking at tree growth, nutrition, yield, and water use in response to that as well. And this is just a list of the sites and their locations, and then what year they were recycled and planted. So we have some differences in establishment year, and the baseline soil organic levels range between 1 and 1.5% to start with. And so each one of these locations has 4 or more replicated blocks, and it's being compared to just total removal of the trees. So moving those trees off site. Seeing as how, looking into the future, burning is going to be such limited application, we think that this is a good control for comparison. Okay, and so really importantly to kind of, I mentioned those models and trying to understand at different application rates, what's the long-term carbon storage potential. These locations, they vary in their dry weight ton per acre application. A smaller stone fruit orchard of a younger age might only contribute somewhere in the area of 25 tons per acre, and a fully mature almond orchard that's 25, 30 years old might be of a much larger scale contribution. So we need to kind of take those type of things into consideration, and then factor in what we think what that would mean in terms of the tons of carbon per acre contributed. We're monitoring some soil, biological, chemical, and physical indicators, both in the drip line and the wetted, both in the drip line where it's wetted compared to the alleyway. So we're trying to take into effect the spatial variability with management. And at 2 of those locations, we're looking at greenhouse gas emissions. Just quickly, some of the data that we've collected so far. So all of these sites, as I mentioned, are less than 5 years old, and we're already seeing differences in soil biological and chemical indicators that are indicative of change in soil conditions. And so with these different graphs, the blue would be those control plots, and then the orange would be plots that received orchard recycling. And just starting at the top, we have soil organic matter. So, almost all of the recycled plots are trending above the control. And we've already seen a significant difference at 5 out of the 8 sites in terms of the levels of soil organic matter. Looking at just the broad microbial microbial respiration, so the level of microbial activity in the soil, we're seeing higher levels at most all the sites and significant at some of the sites. And then and indicative of those pools I mentioned, both the active soil carbon pool and those passive pools. We have measures of oxidizable carbon, seeing higher levels there. And then finally, we've measured what's called autoclave citrate extraction measure, and that's a measure of the protein content in the soil that would be organically bound to nitrogen. So this demonstrates an enhanceability of the soil to store nitrogen. So we tend to think of nitrogen as very unstable, not staying in the soil for very long. This sort of tells you that this is giving you a little bit of a buffer, a savings account of your nitrogen And this indicator, this ACE protein indicator, is also associated with soil aggregation and water storage, some other things that we are also investigating. So beyond those lab indicators, sometimes it's nice to just see, like, what is there something I can see in the field? And so we've been looking at infiltration rates at these sites across the state. And so here's some data from one location, or the blue dotted lines, we have infiltration rates on the orchard berm compared to the control. And Dan Rivers is one of our technicians based out of San Joaquin County, has been traveling all around and doing these detailed infiltration tests. And anybody that knows it, that takes these measurements, this can require some time and precision to get good data. So appreciate the good work he's doing. We are doing some detailed analysis of soil moisture in the tree root zone at one of the sites in Kearney, where we have neutron probes installed. So we're doing, pre and post irrigation measurements and year round, looking at soil moisture changes with depth. Some of the neat things that we're seeing is that we've got much higher soil moisture content by volume in the orchard recycle compared to the control in the top foot, particularly during the dormant period and in the spring before that first irrigation. And then in the middle of the season, even higher levels of moisture retention in the top foot or so of the soil, which suggests that we are getting that greater infiltration, as I mentioned, of soil moisture in response to that orchard recycling. So we're working on trying to understand, if we can get some significant water savings early in the season, kind of building on some of those things that that Allan had mentioned in his talk this morning. Is is there opportunity at some points in the season to capitalize on these added moisture savings that we're seeing? Okay, so quickly, I'm going to try to outline some of the work we've been doing with the greenhouse gas emissions. So again, we're looking at greenhouse gas fluxes to interpret the carbon balance with what's added compared to what's lost. And so a different way of looking at it is the proportion of what's lost as CO2 relative to what remains in the soil. It doesn't even account for what the carbon that's being accumulated in the new trees that were planted. So these estimates will be conservative. And then also, I'm going to talk a bit about the nitrous oxide emissions that we've been observing. Nitrous oxides, much more potent greenhouse gas even than CO2. And so some of the implications of how we might manage some of these replanted orchards to try to minimize those emissions. And then I just wanted to say that these two sites, one is a commercial site. So we just work with, just observing what the growers' management decisions were and accounting for all of those inputs in terms of nitrogen fertilizers and everything to calculate an emission factor, which I'll show in a few slides. And then at the Kearney Research Station, we have a much more better controlled experiments. So there's, good benefits and trade-offs. These are two very closely situated research locations, similar soil type and growing climate. Okay, so it's the two sites that I mentioned. One was established in 2018, one 2019. We have replicated plots comparing orchard recycling to the control. We're monitoring flux both in the berm and in the alleyway. And we're making these measurements prior to and after fertigation and irrigation events, precipitation events, and otherwise weekly. So, year-round monitoring of the greenhouse gases. Okay, so some of the results. So the daily surface CO2 emissions at Block 92, so this would be our more controlled site. So this is showing some of those emissions for the first 2 years. And what you notice right off is that we see big fluxes right when we started monitoring. So this is soon after The recycling was performed, and soon after planting, we began monitoring, and we see much higher, greater than 2 times higher level of emission rates in that first year. With this location, we estimate that there was about a 61 ton per acre initial application. So that would be the equivalent of about 75 tons per hectare of biomass carbon. Sorry for the unit switch on you there. And so this is the initial amount of carbon. This is our estimate of what that carbon loss was in the first year. And then this is the estimate of what that means in terms of what's been retained from what was applied. So despite those sharp peaks in that first year, we really saw things, come down and level off. So when we look at the year 2, in comparison, we see much lower levels of carbon and CO2 loss, compared to year 1. And so after 2 years, we're seeing close to about a 66% retention of what that initial application was by the end of the second season. This is data from the commercial site. So very similarly, we had a bit different estimate on the application rate. We think that that's closer to about a 40 ton per acre application, and found after 3 years of monitoring fairly similar retention rate estimates. Okay, so a precise estimate of all of this carbon balance really counts on understanding what that initial application rate is, and so that has, in a lot of these previous studies, that's been sort of a source of difficulty. So we've developed a shaker sieve table that separates wood chip and debris by soil class, and we take intact cores in the field of a known soil volume, and we're trying to extrapolate over time what that degradation rate is. And so this would be the baseline information of the wood chip sizes at the initial application, and then a comparison over time from 2019 to 2021. And so one of the main things we found here was that with this initial baseline application, aside from what was actually smaller than 0.16 centimeters, the second largest portion of what was put into the soil was actually about 1.27 centimeters in size, so the equivalent of about half an inch. So the majority of what was initially applied was in that size range. But then when we went back 2 years later and looked at the orchard recycling plots in the drip line, that largest fraction was actually in that greater than 0.16 centimeters. So this suggests that there was a rapid decomposition of that larger debris from the initial application. So we're still working on refining these estimates. We need to do more cores again this spring, but close to about a 60% retention. So similar to what that CO2 data was showing us. We're also looking at doing some lab incubations to do some similar things, looking at CO2 and N2O flux, based on the debris size fraction, and then also in the presence of nitrogen. Okay, so in the field, just like in the lab, we're seeing, in the field, just like with the CO2, we're seeing higher nitrous oxide emission peaks in that first season after orchard recycling, and then it's really greatly reduced after that first season. The blue arrows here indicate fertigation events in each year, and so in the orchard recycling treatments, the largest portions of emissions is coming from the berm. So you have this high carbon source in the presence of the nitrogen inputs, and that is stimulating nitrogen cycling processes. We're doing some work to try to tease out what portion of that might be nitrification compared to denitrification. I'd like to do some future work looking at the effects of the type of fertilizer and how that could be impacting it. Okay, so why are we doing all this? Well, in recycled orchards, growers intuitively think, okay, I'm putting in this really large carbon input. That means my carbon to nitrogen ratios are really high. So I need to put on more nitrogen. And so in the case of that grower example that I mentioned, if we recommended for this tree spacing that you put on close to 28 pounds per acre for first leaf, so that would be the standard recommendation, he was putting on over double that. And understandably. This on the left is showing the grower site, and I'm sorry, I apologize about the units, but this amount here would be the amount of nitrogen inputs. And so this accounts for the nitrogen fertilizer plus what we've calculated to be in the water. So this is that grower site. We did a much lower initial application at the what we call block 92, the more controlled site, even despite that higher wood chip application. And so what we're looking at here is what the emission factor would be. And so the emission factor is the amount of nitrogen and nitrous oxide loss in proportion to the units that are applied. And so a small emission factor indicates a more efficient uptake of fertilizer, nitrogen, and reduced losses. The IPCC reports an average of 1% emission factor across agronomic crops, but micro-irrigated almond orchard studies found that this is usually between 0.9 or 0.19 and 0.35 in micro-irrigated systems, because most almond orchards are in California and this very arid climate with very low levels of organic matter. Takeaway is that we found elevated levels compared to the control in that first season. So there's, we're seeing a strong influence of nitrogen inputs in that first year, but then we see a really dramatic decrease in year 2 and 3. So we're actually, it was a little different at this site, but I mean, generally speaking, the grower is going to increase their nitrogen inputs, as the trees grow, because the trees have a higher need. So despite the fact that we were adding more nitrogen in the subsequent years 2 and 3, that emission factor was actually really declining. And so, it's an important takeaway is that the first year is critical. And then looking at the tree growth and then eventually yield in a few of these orchards, we haven't found that fertilizer rate has really impacted tree growth and yield. And so the orchard recycling trees, even at the block 92 site, actually where we have a variable rate nitrogen trial, they actually perform better than the controls, even at the lowest nitrogen rate. But some growers have reported stunting after planting. And so our data points to the idea that application timing is more critical than fertilizer rate. And again, this is an area of study that I would like to continue to pursue. So in conclusion, whole orchard recycling, it's demonstrated many positive benefits as an organic management alternative. We are seeing higher emissions in terms of CO2 losses in the first year, but the carbon storage benefit of orchard recycling is going to be greater than burning disposal. And then we found that majority of that losses in the first season, and then it slowed to about a 4 to 6% loss in year 2 and 3. Our decomposition estimates are consistent with those estimates, but we need more data. Our regional soil indicators, our growth and yield show that the orchard recycling treatment enhances soil function. So we're going to continue to monitor the changes in soil carbon to inform the models on those long-term estimates. Large carbon content in wood chips drives growers to apply higher nitrogen rates than what's recommended for first-year trees, but our trial data has found no benefit in terms of growth from those excess applications. And then we tend to see high peaks of the nitrous oxide emissions in response to fertigation, but then that's drastically reduced in year 2 and 3. And so we'll be continuing our analysis of greenhouse gases, soil carbon levels, and other variables. And hopefully this information can be used to improve predictions of the long-term carbon storage benefit of orchard recycling. And sorry for going over.
Okay,
Thanks.
May, thank you. Thanks so much. We are a little bit into our break. We will be going on break now for 7 minutes, starting again at 11:10. But May, you do have quite a few questions in the Q&A, so you can either answer them over chat or live for those who want to stay on. And for anyone who put a question in the chat directly, please do move that into the Q&A so our speakers can answer. I do see that all the speakers from our session are on still. So if there's other questions that are in, hopefully you can drop them in the chat and they can answer them then. But thank you again so much to our 4 speakers. This was a really great session. Thank you to Dr. Lauren Hale for co-organizing this with me, and thanks for your attention.
Welcome back, everybody. We're about to begin our final session for this year's conference. My name is Nick Clark. I'm a farm advisor with UC Cooperative Extension. I'll be moderating this session, and the co-chair for this session is my colleague, Dr. Daniel Geisler, Nutrient Management Specialist up at UC Davis. So if there are any issues, Daniel has agreed to jump in and rescue me. We have 3 speakers for you today, and then the conference is over. I'm going to start by introducing our first speaker, Michelle Leinfelder-Miles. Michelle is a UC Cooperative Extension Delta Crops Resource Management Advisor. She serves several counties in the Sacramento-San Joaquin River Delta region. Her educational background is in crop science as well as horticulture, and although her research in her career has ranged from soil management and crop production of several orchard crops, more recently her research and extension work with UC Cooperative Extension focuses on agronomic crops and water and soil resource management. Today, Michelle is going to share with us some recent results from her work on crop rotation and fertility following whole orchard recycling. So a great follow-up on May's talk. I'm going to be quiet now, and Michelle, the floor is yours.
Great, thank you, Nick, and thanks for the introduction. Okay, great. Thanks again for the introduction and for the opportunity to present today on this work that I've been collaborating on with Dr. Brent Holtz and Dr. Mohammed Nouri in San Joaquin County. And yeah, I feel really fortunate to follow up on May's really fantastic presentation. This work that we've done looking at nitrogen fertility in common beans following whole orchard recycling is, it tags on to the work that Brent and May and others have been doing for many, many years. This work isn't quite as data rich, but I hope to provide some practical information for growers and consultants, not only with the data that we have, but also with some grower observations that we've come to learn. So let's see. I've got a few introductory slides, but May did such a great job. I'll be really quick on these. Of course, whole orchard recycling is the process of chipping up and spreading and incorporating an orchard that's become unproductive, adding those wood chips back into the soil, and the importance of it, especially as air quality regulations have limited the grower's ability to manage their tree waste, if you will, with burning. The benefits and the challenges of WOR, or whole orchard recycling. Benefits include soil health, like enhancing the microbial community, and water infiltration, as May showed with her data. But a challenge, I think, is managing that woody biomass given the high carbon to nitrogen ratio of that biomass. So with a high carbon to nitrogen organic amendment to the soil, it means that initially the nitrogen is primarily used for microbial energy and maintenance. In other words, that nitrogen is tied up. It's being used by the microbes, and this can impact the nutrient availability for the subsequent crop. Our understanding of whole orchard recycling is best understood where all of that rich information and data have already come from, which is almonds being recycled back into almond orchards. In this case, we had a really fantastic opportunity to look at a very different system that didn't involve almonds at all. So in this case, our grower over near Linden, California, in San Joaquin County, was really familiar with Brent's previous work in whole orchard recycling. And this provided an excellent opportunity to design the work, even if quite quickly we needed to get on this opportunity. And so the grower reached out to Brent and said, what would be helpful for us to learn from this opportunity. And so we were able to leave some areas of the field without wood chips. And I'm going to show a schematic of our research in a few slides. But by having, in a grower field, having a control was a really great opportunity where there were no wood chips. So here's a couple photos showing the recycling took place in June of 2019, and it incorporated approximately 70 tons of wood chips. This was an all old walnut site, and so the amount of wood chips being incorporated was a bit more than what May was showing for almond. And you can see the thickness in that picture on the right. You can see the thickness of the wood chips that was applied on the top before it was incorporated. The wood chips can vary in size. And so again, that same photo from the previous slide is now on the left. Most of the wood chips are of that size, which are, you could call it a mulched sized wood chip, but there are some larger pieces of wood that don't get broken up as well. And so of course, this influences how quickly the wood chips are broken down, the size of them that is, and can influence other soil properties, not only the nutrient cycling, but the water infiltration, and potentially the future groundwork that the grower needs to employ. So at this site, the grower was especially interested in employing practices that would hopefully mean he wouldn't have to fumigate the soil before replanting back into another orchard. And so in this case, he cover cropped with a brassica over the winter season of 2019 and 2020. So after recycling in 2019. And then, in fact, he didn't get his trees or just other things arose. And so we were able to continue this study for 2 years. And he also cover cropped in the winter of 2020 and 2021. So you can see in the background, the brassica cover crop was very vigorous. And then you can see here, Mohammed took these pictures of the microbial colonization that was happening in that first winter season. Of course, this cover crop was also adding biomass to the soil. So then our objectives were to evaluate a few soil properties and then also the dry bean yield from the subsequent crop that was happening in the 2020 growing season. And based on some of the previous work in almond, we hypothesized that the bean yield might be reduced following the whole orchard recycling due to a nitrogen immobilization. But that potentially we could overcome any kind of yield gap with additional nitrogen fertilizer. So a real applied project here. This is a schematic of our trial. You can see the green squares are labeled control, so that's where there were no wood chips. And while the whole field actually, except for those green squares, was a recycled field, but we isolated our sampling area to those orange squares that are adjacent to the green squares. So that's what those mean. And then we implemented these strips of a couple different nitrogen fertilizer rates that were applied at the side dress application to learn whether an increased amount of nitrogen fertilizer would be needed to overcome any sort of yield gap that might happen due to nitrogen immobilization with the whole orchard recycling. So those green control plots are about a ½ acre. So we had a decent sized sampled plot to sample from. And those strips are the length of the field, and we're about, let's see, 9 beds wide. So nice big plots. This shows the different nitrogen amounts and fertilizer rates that we employed in this trial. So in 2020, the grower applied what he normally applied to his bean crops when he was growing beans in the past. And you can see that 2020 standard rate, or the grower rate, had a total amount of nitrogen for the season of about 116 pounds. And this aligns well with the UC dry bean production manual that estimates that a bean crop needs about 80 to 120 pounds of nitrogen to produce a 2,000 pound crop. Now, beans, as I think we all know, are nitrogen fixing legumes, but they don't fix enough nitrogen to produce what they need to sustain them and to produce that 2,000 pound crop. So that's why nitrogen fertilizer is still recommended in bean plants. Our doubled rate in 2020 basically was just a doubling of the side dress rate, and put on about 204 pounds of nitrogen over the course of the season. In 2021, when we were fortunate to be able to repeat this trial, the grower decided to postpone replanting an orchard and planted beans again. In that case, our rates were a little bit less than in 2020, but we still doubled up that side dress rate, so we could look at that difference in rate there. In 2021, however, you'll see the data in just a moment. The grower had kind of a bad experience in 2020, and so instead the grower's rate was actually the doubled rate in 2021. So here I'm going to show some pictures first, and then I'll show the data. In August of 2020, this was, I think, the day before the side dress application, I took these photos. The beans were noticeably pretty yellow across the whole field. And then the pink flags indicate the separation between the recycling and the control. In the photo on the left, the pink flag that's in the foreground, everything to the right of it is in a control plot. And then on the photo on the right, the pink flag that's also in the foreground, those beans closest to you in the picture are also in a control plot. And I think hopefully it's obvious, it certainly was obvious when you were standing in the field, that there was stunting happening in the recycled area of the field, and the beans in the control area were doing much better. As I said moments ago, all of the beans seem to be a bit nitrogen deficient across the whole field, regardless of being in a control or a recycled area. But certainly the recycled area, the beans were struggling a lot more. And I just realized another point I wanted to make. So some of the grower observations, in this first year after recycling, the grower had a harder time with irrigating. So this is a furrow irrigated field for the beans. The water was not moving down the furrows very easily. It was infiltrating pretty well and therefore not moving down the furrows. And the field wasn't drying out very easily between irrigations. So it made it difficult to employ some of the other practices the grower needed to do, whether it was cultivating or putting on pest management sprays. The ground just took a lot longer to dry out, and some of the operations got delayed for that reason. In 2021, this picture was taken about in probably mid-July, so a bit earlier than the previous photos. But certainly in 2021, we were noticing a much healthier bean crop than what we were noticing in 2020. So already, just by observation, it seemed that whatever impacts may have been happening with the whole orchard recycling in 2020, those impacts weren't continuing into the second year after recycling. So now some of the data. We looked at organic carbon, soil organic carbon, and total nitrogen. We also looked at nitrate and then bean yield. I'll get to those in just a moment. But here on this slide, if we focus on the graph on the left first, and if we focus on the blue bars, those are the data from the fall of 2020. And what we see is the soil organic carbon was statistically lower in the control plots compared to the whole orchard recycling. These data come from about October, right before harvest. And then if we shift and we look at the orange bars, that is the organic soil from the second year after recycling. We see that, again, there's still that statistical difference between the control plots and the whole orchard recycling plots, and that it's continuing to grow over time, which indicates the wood chips are breaking. Some of those larger wood chips are probably still breaking down and contributing to the carbon pool. Of note, the control plot in 2020, in the fall of 2020, basically, there was no change in soil organic carbon. I suppose you wouldn't really expect it since they didn't get the wood chips, but given that I mentioned the cover cropping, I just wanted to point out that we weren't seeing an increase in soil organic carbon from earlier in the season to that harvest season soil sampling. That basically stayed constant. Now, if we shift our view over to the total nitrogen, again, that control plot didn't see an increase in total nitrogen by fall of 2020. That's basically where it started and where it finished the season. But certainly we saw the increase in total nitrogen in the recycled plots. And then if we look to the orange bars, certainly the total nitrogen improved in both control and in whole orchard recycling, and probably in those control plots, it's in part due to the cover crop that was planted over the winter seasons. The whole orchard recycling had an opposite impact on plant available nitrate in the first year. So if we focus in on the blue bars right now, in fall of 2020, there was certainly the plant available nitrate was limited in the whole orchard recycling plots. And I think the picture that I showed earlier in the slideshow indicates, the data and the picture are showing a similar impact. Less plant available nitrogen and stunted plants in the recycled plots. If we look at the orange bars, though, in the fall of 2021, we see the opposite. So the plant available nitrogen is higher in the whole orchard recycling plots. And I was a little bit confounded by this. I've still been, the data are still relatively new to me. We've been only, starting to analyze them and thinking about them. But I'll be glad to talk with May about it, because I think she saw similar results over time. The plant available nitrate is improving in the recycled plots. And I suppose that could be related to that total nitrogen with the organic forms of nitrogen in it. is breaking down, mineralizing, and becoming available for the plants. So perhaps that's what we're seeing over time. So now yield, here's where the rubber meets the road. Whole orchard recycling did impact bean yield in 2020, but it didn't in 2021. And then I have parenthetically, at least not in a statistically significant way. So again, first honing in on those blue bars, in 2020, our bean yield suffered as a result of whole orchard recycling. And bean yields there in the control plots were probably about average, but certainly suffered as a result of whole orchard recycling and probably that nitrogen limitation that was there. But by 2021, we didn't see that kind of impact. There was perhaps a trend for there to be a little bit lower yield in the whole orchard recycled plots, but statistically, due to plot variability, we couldn't tease that apart as being an actual difference. And then I haven't been presenting data on those two nitrogen rates because they haven't been statistically significant up until now. So with the soil, they weren't statistically different. And therefore I just presented the control and the recycled bars. But in this case with yield, there was a significant difference with those nitrogen rates. So here they are. The control plots, if we want to say that's kind of the normal, then we don't really, if you look at the 2020 graph on the left-hand side, we didn't see that doubled rate, at least statistically, didn't improve yield in the control plots in 2020. However, the doubled rate in the whole orchard recycled plots at least made the yield of those plots statistically comparable to the yield in the standard nitrogen rate of the control plots. So I guess what I'm trying to say here is that doubling the nitrogen rate at side dress seemed to improve the bean yield such that it was comparable to the control plots. I think what the data show from 2020 is that there was probably an opportunity to maybe try an additional nitrogen rate a little bit higher than what we applied. And hindsight in research is always 2020 and woulda, shoulda, coulda. But in this case, I think we showed that it was important to apply more nitrogen, and whether even more nitrogen on top of that would have been of benefit. That's where, you know, we hit a roadblock and we can't really speak to that. But I think, you know, people looking at this data would certainly question that if I didn't say it. So then if we look at 2021, we don't have any statistical differences across these nitrogen rates. However, there was still a little bit of a trend in the recycled plots. You know, you can see those bars have a little bit larger error bars in 2021 compared to 2020. And that resulted in no statistical differences among the different rates and across the recycled plot versus the control. But I wanted to point that out and show those bars separately because of that trend, even though there were no statistical differences. And certainly by 2021, the overall yields for the field were much higher than in 2020. The second year after recycling, we saw those yields go back up compared to the lower yields that the grower experienced in the first year after recycling. So to summarize, whole orchard recycling has the potential to improve soil health, but it seems to present challenges, whether it's for a subsequent orchard, as May has presented, but also it seems for annual crops like what I've shown here. I think, you know, this is really a case study for what happens in an annual crop following whole orchard recycling. I also think that it's a case study for an orchard that is not almonds. So we have a lot more opportunity with whole orchard recycling to do research with different orchard crops followed by different annual crops after the recycling. In fact, my collaborator, Mohammed Nouri, is going to be looking at a recycled cherry orchard coming up here in the next couple of years. And so it'll be interesting to see to follow that site. It will be replanted back into cherry, I believe. So he's going to be looking at a recycled cherry going back into cherry. And these sorts of things are, kind of individualized, but contributing to the overall knowledge that we have on whole orchard recycling. So I've listed just a few of the key points that we found at this site with a walnut recycled orchard followed by beans, higher soil organic carbon, total nitrogen. I think this is a consistent thing that we're noticing in recycled orchards. Lower plant available nitrate in the first year, but higher nitrate in the second year. So we may be seeing that organic nitrogen being mineralized and becoming more available by the second year. Lower bean yield in the first year, but doubling the side dress rate seemed to help overcome the yield gap that was imposed by whole orchard recycling. Certainly, this is not a prescriptive rate. I'm not saying that 200 pounds is a magic number. I'm just saying that this was what we were able to look at this site, and certainly growers will need to tailor that based on previous experiences, based on their soil types, based on the trees that's being recycled and the size of those trees, the amount of woody biomass that's been incorporated. But bean yields seem to recover by the second year after recycling. And with that, I'll just thank you. I have written up the first year of this trial. It's available from my website, which is listed there. I haven't been able to write up the second yet, so that report will be updated as soon as I can get everything summarized for that report.
Thank you very much for that wonderful presentation, Michelle. And Michelle's an excellent researcher. I like her approach. She looks at what others are doing and says, yeah, but what if this other thing? And then instead of just sitting in her armchair, she goes out and tests it. So very, very cool early study. Michelle, we have some time for questions. I'm going to field them to you in the order that they've come in. And then, of course, if we run out of time, you can hopefully answer them by writing. The first question that's come into our Q&A is from Richard, one of our attendees. Richard asks, do you think that the plants could have been already stunted by the time of side dressing, and that is why the N applications had less of an impact?
Well, yeah, I mean, we saw that certainly. The picture that I showed from August of 2020, that was taken either just before side dress or the day before side dress. So certainly the plants were stunted already. I think, the side dress application, this was, the plan of attack had already been established, right? So we knew that we wanted to put forward these 2 nitrogen rates based on the almond work that had been done, that Brent had been doing in almond, recycled and then replanted back to almond, where he did in some orchards find a benefit to doubling up the nitrogen rate in that subsequent orchard. And so following that theme, we developed this project to look at that. So the plants probably were already stunted, and then we applied a nitrogen rate following, the grower's practice of having grown beans for many years in the past, and then doubling up what he would have usually done. So what's the grower doing? And based on previous research, our hypothesis of what we may need to do in order to produce a good sizable bean crop.
Thank you. Okay, a question that came in to our chat from Bob Beatty, our walnut physician, asks, could the vegetable crops nitrate and quick test help to monitor available nitrate during the first year in order to fine tune the nitrogen application requirements?
Yeah, actually, that's great, Bob. yeah, again, coulda, shoulda, woulda in some cases. But certainly, and I think that comment or question ties in well with the previous question that, maybe we could have been a little more nimble. But again, sometimes there are constraints on the grower. So our doubled rate was essentially the grower being able to make a second pass over the rate that he was already doing, or slow up the tractor by half the speed, right? So we were trying not to impose too much of a burden on the grower from what the normal practice would have been. And hence the doubled up rate was a way that we could have something interesting to look at and compare to, but not put too much of a burden on the grower to impose an additional practice that would be hard to implement.
Nice. Thank you very much, Michelle. That's our time for your presentation. You do still have a question that came in a little bit late in the Q&A, and Sharon Bennis has some questions for you in chat. So hopefully you can address those by writing.
Great.
I'd like to introduce our next speaker, Hossein Zakeri. Hossein is an associate professor at Chico State University. His educational background is in crop breeding and agronomy and crop physiology. His research work has focused on row crops ranging from safflower, wheat, lentil, peas, canola, and soybean. So very broad spectrum of crops that he's worked on. Today, Hossein is going to share with us his work on legume, food, and cover crops in California. Hossein, the floor is yours.
Thank you very much, Nick. Let me see if I can share my screen. Well, thank you so much. Thank you for the introduction, Nick, and thank you for inviting me to this presentation and giving me this opportunity to share some of the work that we've done in the past few years on different legumes in Northern California, and now it's a little bit farther than Northern California. The title of my presentation is very broad, and it's basically we're looking into ways and approaches that we can promote legumes in California. On the picture, it's my colleague, Dr. Kyle Brazier, that did most of this work, and I'm hoping that I presented good for him. He is still working with me, but his main job is managing research units of willow marine seeds based on salinas. And on the right, it's me taking a picture this summer with a tiny pomegranate that is left from my dad's orchard. I visited the country after 15 years, and the huge orchard that we had, this is what is left from it due to the drought. So going to legumes, before I go to my project, basically, legumes are known for many things. The word legumes is connected to many positive things when we think about it. Basically, it's a great food. If we eat it, we feel good that we've done something for environment and we've done something for our health. They are very well known for to being the meat of poor people. I've just borrowed these two charts to show that how bean production, if we know bean as the representative of legume compared to wheat, in different countries. And for example, United States compared to low income and low deficit and food deficit countries, can see that in terms of wheat, we move neck to neck, pretty much close. But when it comes to bean, those countries are rely on mainly they produce much more bean than what we do. And the reason is just not food, because that's also the source of their soil nitrogen. Beans are capable of nitrogen fixation. And one of the things that has happened in the past, especially here in North America, is diversifying cropping system by adding all kind of pulse crops to our cropping system, especially in the northern states and in Canada. So there are so many benefits in beans and legumes. Now, if we look in California, these are the data from 2018 and 19. The area harvested in 18 and 19, you see it's about less than 50,000 acres of bean. And then in 2019, it shrunk by about 50%. When I was looking into these data, I thought, oh, our program is working very well. We shrunk the bean production in California. But in terms of value, dollar value that is generated, it's very, very low compared to many other things that we've seen. We actually, in dry beans, we rank 52nd in the nation. I guess that would makes us the last. And if we look into reason, we might find so many reasons that why beans are not grown, or in general, we don't have pulse crops here. Well, competing with these high value crops is not easy. And another thing is the low yield of beans and legumes in general compared to other crops, because they spend so much energy in fixing nitrogen, they're normally low yield. So the whole program that we have, and whatever I have to present to you is rather it's just finding ways to promote them than providing some technical approach and showing you how to do this, how to do that. We are looking into potential, and I'm just going to share with you the avenues that we think it's possibly can be used to promote these crops in California. I'm going to summarize the result of 3 projects. One is fava bean as cover crop. The second one is growing fava bean as vegetable crops. And the third is the alley cropping of beans between young orchards. On the picture here, on the top, you see bean growing between young almond here in Chico. This is a work that we're working with a farmer here in Durham, California. And at the bottom is a picture of some of our new fava bean lines grown between oats and other cover crop mixes. But fava bean, I'm sure you've heard of it from us or from other people. It's a very popular cool season crop in the world. In California, it can grow easily with no or minimum irrigation as cover crop. And if you want to harvest some of their pods, you may have to do 1 or 2 irrigation. It significantly increased nitrogen fixation. And it's very diverse in terms of seed. The majority of fava bean that we've seen in the market and our understandings are these large seeded ones that are food variety, but medium-sized one. A good example would be bell bean that we use it as cover crop. And also there are so many smaller seed ones that they all belong to the same species. And our research shows that they perform pretty similar to large seed ones. So one of our goals in our future research is to see if we can shrink the size of seed to reduce the seed cost of cover crops and also help with planting it in the field. A quick comparison of nitrogen fixation of pulse crop. This is a study that Fran Wally did in 2007, summarized the nitrogen fixation of multiple pulse crops. A good takeaway from this picture is that you see, like, from 80 studies on pea, lentils, dizzy, and kabuli are 2 types of chickpea or garbanzo. One of the thing is that beans normally fall in the lowest category when it comes to the nitrogen fixation, and they are known to be the laziest for nitrogen fixation. And on the other hand, we have the fava bean, which is much higher. Another picture from this publication that I thought it's worth sharing is that this misconception that some of us have, misunderstanding that we think whatever nitrogen is fixed, it remains for the next crop. That's not the case, because once we harvest those grain and we remove them from the field, what is left in the soil is pretty much nothing. This picture shows the nitrogen change in the soil after harvesting the same pulse crops. And you can see that the majority of them basically don't leave any nitrogen in the soil once you harvest them, or their impact is very minimal. But in compare, when you look into fava bean, it's basically, it's about 60, 70, 80 kilo per hectare nitrogen adds to the soil. One of the first observation that I had when I came to California was seeing fava bean grown in Lumber family farm in this saturated soil with water. We visited the farm, sampled the farm multiple times, and quantified the amount of nitrogen fixation. This is a picture of their field that I took in March 21. And these are some of the data that we did in 2 years from 3 fields. And in that clay soil with saturated condition, you can see that anywhere from 30 to 75% of fava bean comes from fixation. So it does really good and impressive job in nitrogen fixation. So with that, to start the project, myself, Margaret Smither from NRCS, Dr. Rior from Fresno, and Kyle, we started thinking that what's the best to start, and we decided to see what's out there and look into the diversity of fava bean in the country. So our first project was we planted 63 fava bean lines that we got from the Pullman Research Center, planted them in Chico and Fresno in 2 years. And we look into so many different traits and factors that were important, and we thought it is important. I'm not going to go through all these data. I'm just going to show you how diverse this population is. And what we found that there is something for everyone if you're interested to grow fava bean for many things. In terms of height, the majority of them are fall in a taller one, but we also have some short varieties. Flowering dates, we have a very wide range of flowering dates, seed size, N yield, and NDFA. The difference between N yield and NDFA is the proportion of plant nitrogen that comes from fixation. N yield is whatever nitrogen is left in the soil for the next crop or produce for the next crop. Nodule count, harvest index, biomass. I like to use this picture and show how big this crop can get if there's enough water. This is 2019 when we were poured with rain, constant rain and a good soil. It grew crazy. This is another picture that shows the flowering span of this population. It provides a good resource for pollinators during winter. As you see, the fava bean was planted in November and it started flowering way before end of January. So there is chance if a mix of these panel is planted, it can produce or generate flowers for a good amount of time during winter when flowers are not around for pollinators. So that's one thing that we measured. Another interesting part of this work that we did in California, Oregon, and Arizona and Nevada, especially those drier areas that we wanted to see how these perform. We compared bell bean, which is currently used as cover crop, with some of the other materials that is being held or developed in ARS. And as you can see here, most of those perform better than bell bean in terms of biomass production. So the result is not suggesting any specific variety. What it shows is that it is potential to improve the performance or benefits of fava bean in cover crops for areas that are limited for water. Another outcome of this study that I think is very applicable for growers is that if you're growing fava bean and you wonder how much nitrogen you're getting, we found a very direct relationship between plant height and biomass, which is very interesting. And biomass is also linked to total nitrogen that you get from fava bean. So getting plant height is a very good way of looking into the benefits that you get from fava bean. If you're interested to see the seed size and seed form, seed shape and color of these 63 lines, you can check our website at favabeanresearch.com and take a look at those seeds that are available. And their characteristic. A few other things that we measured and I'd like to share with you is the kind of disease and pest. We quantified them. I don't have a data to present, but I just thought I'd better show you what's going on. When we get a ton of rain, normally we battle with chocolate spot pretty much all over the plant. That's the one that you have here. In a drier year, it tends to be more aphids on the plant, and in some years it gets really, really bad. So these are two major challenges of growing fava bean here that we observe. Now, after finishing that first study, our goal changed. So to see if we can find something smaller than bell bean and to mix with these cover crop mixes that we grow here, because that's the largest seed that we grow. It costs more and it's not always easy to use a drill to plant them. So we selected a couple of small seeded ones to compare them with bell bean, and we currently are growing them in multiple locations here in Chico, in Fresno, in Salinas, Pomona, and we also have field in Phoenix, Arizona, specifically a grower in Arizona we work with. They want to see how these fava bean improve the forage quality. We also are planning we started working with someone in US Virgin Island to check this in a different climate. And as I said, the whole purpose is that to compare the small seeded ones with bell bean in different cover crop mixes. Our field trial in Chico looks really nice. So if you are around and you want to stop by and take a look at it, you can see how these lines are grown in different cover crop mixes. These are some of the sampling that my student did just last week, different lines. What I have here is the 100 kernel weight. So this one is bell bean, 45 grams. The 100 seed of bell bean is about 45 grams. And as you can see, these are all smaller than bell bean. What we do, we harvest them, we take a look at the nodules, we measure nitrogen, and we measure a whole bunch of variables. This is just a start. These data shows nothing. I just want to share with you what we are doing with them. Leaf surface area. We measure their competition. That kind of shows that how they compete in different mixes. So I have their leaf surface area in orchard mix and in oat only. We also counted nodules on them to see how much their nodulation changed. We have the information from fava bean only. Now we want to see how they perform in mixes when they need to compete with other species in the cover crop mix. With that, I want to switch and move to another avenue that we've been working on it to see if there's any area to promote fava bean as food crop. And surprisingly, we found out that fava bean is a food crop in the world. Some people eat it. I gave it a survey last year to this conference, and I have some results to share with you. But I thought I should start with showing you some of the nice, good-looking. It's time for lunch and show you what you can make from fava bean. Just want to say you, if I was back home in Iran in these cold days, when I walk in the street, one of those foods that you would get is just some fava bean that they boiled, and you can get a bowl of it and eat it. So with that in mind, we started another project to see what is the potential of fava bean as dual purpose, to grow them, harvest some of the fresh pods, and then terminate them as cover crop. Would it work or not? So we designed this experiment in multiple locations that we had multiple harvests from different plots, different varieties, and different treatments. So we would either not harvest anything and we would leave it as a cover crop, or we would do just one harvest only, 2 harvests, or 3 harvests. And then we, after measuring their pod production here and quantifying the amount of pod, we would just terminate the crop and measure their total nitrogen and leftover nitrogen. This is the only chart that I have for this experiment so far that has been analyzed. As you can see, the amount of pod production by these varieties are significant, up to 80,000 kilo per hectare. Fresh pod can be harvested from these varieties. And of course, there's variation from variety to variety. Agua Dulce, Grano Violeta, Masterpiece, Varoma, Windsor. Let me show you these pictures. So just you have a picture that how these guys look like. This is Agua Dulce, Grano Violeta, Masterpiece, Varoma, and Windsor. And then this is their performance. If you're interested in early pod production, you may have better luck with either Varoma or Grano Violeta. If you're interested in late production, there are other varieties that they produce more later, like Agua Dulce and Windsor, they have more later. So there is different. We also have measured a whole bunch of qualities in these pods. I don't have them to share with you in terms of sugar content, moisture content, nitrogen, protein content, that hopefully soon we will publish those, so it will become available. A few other things that we've learned in terms of promoting fava bean. This is the result of the survey that people in this conference answered. There is obviously some interest, at least to try some of these foods that are made from fava bean. My favorite one got the lowest score. I'm not offended, that's fine. But just to show you that how many variation and diverse food are available that we can make from them. And we had a student who finished her master on this study and found out some good results that people are interested. And this is the answer that you provided to me. What we found is that there's not a very good way of finding information about this crop. Our knowledge is mainly comes from our connection with people. no good resource of information about food and how to cook them, how to prepare them, and what to make from them. We've done some outreach. There's quite interest when we go to farmers market. People love to hear about it, love to hear about their health benefit to soil and their food possibilities. We give away seed to people at different farmers market. This is the work that we're doing with Lydia Breen down in LA. She's been visiting different farmers market and sharing seeds, giving seed to people and following up with them with food recipe. So this is a huge outreach that we've done and in order to promote it in California. Another part that we've done, we've worked with nonprofits and industry. This is our demonstration plot at Sierra Nevada that we work with them. This nitropical fixation was on their shelf for a few months. So keep your eyes open for next year. Hopefully they will make it again. If you see that beer in your shelf, that comes from fava bean. So this is another part that we've been doing to promote it. Well, moving from fava bean to alley cropping, I have a few slides of the work that we've done with Dax Kimmelshoe here in Durham, California. He's been doing alley cropping for many years, growing different types of beans depending on the market between young orchard. We gather some information from him just to give an idea how much farmers can make from alley cropping. So these are some data that we got from Dax. From 6 years of growing beans in different orchards. Usually he does it in year 1 and year 2. A cost about $600 per acre, and these are costs before this inflation. Average yield about 2,800 pounds per acre. Gross sale about 1,500, so it leaves him and the orchard growers about $900 per acre. So these are the dollar benefit of alley cropping. Now, one of the biggest challenge toward alley cropping is for people that they are worried that, oh, if we do this alley cropping, it may hurt the long-term tree production, or it may introduce pests, or it may hurt the production. So one of the work that we did, and these are just some preliminary data that I haven't analyzed them yet, that we measured the stem water potential of young trees that either were alley cropped or bare land. And by looking into it, there's not much significant difference between the two. So basically growing beans between them, between the trees would not hurt the trees or would not affect the trees' water potential. We've also measured soil moisture content in the same area, and we didn't see much variation. One of the things that we did with Dax is we used one of his orchards and we grew fava bean into it, and fava bean did great in that year with minimum. I think we just irrigated it once or twice, and the rest was rain. This is what we harvested, about 12,000 fresh pot per acre, pound fresh pot per acre of Windsor and Varoma varieties in this field. And as you see, it's growing really good with minimum or not much work to be done. We've quantified nodulation of fava bean, and we have some data for nodulation. And if you ever grown fava bean, you can look at the root that you see that it has the largest nodule compared to other legumes. It's huge. And that may be one of the reasons that it's capable of fixing so much nitrogen. My students spend so much time counting them, and we quantified this. So another thing that we did, work with our engineering department to see if we can develop a software to do it for us. So Dr. Salehi and his student, who is now a PhD student at Davis, developed a software for image analysis to take a picture of these roots and quantify nitrogen nodulation. So the software is almost ready. We're in the phase of publication. When take a picture from the root, it gives you a wide range of data in nodule width, length, and nodule size that can be also used for other things. I'm sorry if I run too fast. I think that was my last slide. Before I finish, I want to thank you to all those people, including most of you in this society, to help me in the past few years to figure out what to do here. especially Margaret and her team at NRCS, Dr. Rior in Fresno, and Dr. Fox in Pomona. I want to thank you people at Pullman and people in Canada and Long Bear Family Fund, and especially Dax and Lydia, who've been helping me in the past few years. And with that, I'm done. I don't know how fast I went, Nick.
Thank you very much, Hossein. Wonderful presentation. We don't have time for you to address the questions live, but you do have a number of questions in the Q&A, and there's also a question from Bob Beatty for you in the chat regarding water. So Hossein will answer those questions by writing. Thank you very much to everybody for asking those questions. I'd like to move on to our next but final speaker, Jairo Diaz. He is the director of the UC Desert Research and Extension Center in Holtville, California, which is in the Imperial Valley, the very southern border of California. His educational background is in agricultural and water resources engineering. His research work for the last 6 years has focused on crop suitability under California desert conditions for several vegetables and evaluating irrigation and fertilization best management practices. Today, Jairo is going to share with us his work on irrigation and nitrogen fertilization outcomes in onions.
Thank you, Nick. Thank you for the introduction, and thank you, Hossein, for that great presentation. I'm really hungry, right now. And hopefully, I can eat some beans pretty soon too. So, in order to eat those beans, I really like to chop some onions too for the sauce. So, as we have been talking today, about the beans, and all the nitrogen fixation. We're going to talk right now about the onion response to irrigation and nitrogen rates here in Imperial County. I wanted to acknowledge, my two collaborators on this journey for the last almost 6 years. Roberto Soto from Universidad Autónoma de Baja California, just across the border, and also Daniel Gisler, the co-chair of this session, and also from UC Davis. Okay, so where we are located, we are here in Imperial County, in this beautiful corner, with Arizona and Mexico on the border as well. So we pretty much, we have around 500,000 acres of irrigated land. We only have about 3 inches of rain per year, so we depend on all the water allocation from the Colorado River for these 500,000 acres of ag production here in the valley. Our summer is pretty harsh, about more than 110 degrees, but our winters are pretty mild. So we are the off-season, salad bowl for the states, and also we export a lot of these commodities as well. Here in Imperial County is a very diverse ag production. We have more than 80 commodities, and we are one of the top 10 counties in value, in ag production in the States. As I say, we relied on the Colorado River water. The Imperial Irrigation District handles the largest allocation of this, about 3 million acre-feet of water on an annual basis. But the Colorado River has been, in drought for the last 22 years. So we pretty much, we have a big refrigerator, but it's empty, pretty much. The larger reservoirs, the Mid and Powell lakes, are only at 30% capacity right now. And so next year, Arizona, Nevada, and Mexico are going to get the first cuts, due to the lower volumes of water in those lakes in the system, So that's going to impact, the agriculture pretty much, on those states. Arizona, I guess, is going to be cut by 18%, the water allocation. So meaning that they're going to have a lot of fallow land over there, or transition to less intensive irrigation crops over there as well. One of the things here in Imperial County, this is a beautiful county that, all the hydraulics on this county, meaning that the water can run, from south to north and goes everything, to the Salton Sea. All the excess of water and drainage, go to the Salton Sea. So the Salton Sea is the largest lake that we have in the state, and it's one of the most pollutant lakes right now in Salty Lake. So due to the runoff from the ag fields, and also from the Mexico side as well, we have some sewage and other things coming down to the Salton Sea. So It requires a major investment, in order to recover this Salton Sea. There is a lot of transfer also of water. There is the largest transfer of water from the ag sector to the municipal sector, in LA and in San Diego. So those things have been reducing, the water that is coming to the Salton Sea. So big issues that we have here, and in order to move forward, water conservation and nutrient management in the ag sector in Imperial County. So let's gonna talk about onions. So onions, California is the largest onion producer in the nation, and here in Imperial Valley, we have about 13,000 acres of onion. And depending on the market, of the year of the market, the value is between $50 to $100 million. So it's a pretty sizable, market for onions. But onions are so diverse, goes from fresh market to processing. Most of the onions are on conventional fields, but some are produced on organic as well. But because it's a low process for development, there is a lot of pressure with weeds on these organic fields. Bed configuration, we have the 40-inch beds, they're kind of the normal, but also due to the pressurized irrigation systems with drip or sprinklers, growers are moving to 80-inch beds as well. So more efficient systems with 80-inch beds. Plant density could be from 4 to 12 lines of onions. And as I said, irrigation systems varies, depending on the needs, but pretty much, growers start up with sprinklers and then transition to 4 or drip or keep up with the sprinklers, through the season. The onion season here in the valley goes from October, when we sow the fields, and we harvest those in May approximately. But the last 2-3 months of the onions is where everything happens, with biomass and uptake of nutrients and water as well. So it takes about 200 days, for sowing to harvesting the onions, but the 2 or 3 months are the most critical, for management. And one of the things with onions is the shallow root system. Less than 1 foot, is where we have most of the spreads of the onions roots. So meaning that it requires, timing and amount of water and fertilizers, on a really rigorous schedule in order to be efficient and conserve water and fertilizers. So on these charts, I just wanted to show you, how slow the crop grows here in the valley. So we started, last week of October, and it takes, about 120 days for the bulb, the diameter of about 1 inch, the bulb to start developing in this one, about 6 to 7 leaves where we have at this stage. So the biomass is pretty much minimum at that stage, but then it's so progressive, in the next month, and then we have a boom of biomass and the bulb, forming aggressively. And at the end, we just ended up with most of the biomass, towards the bulb, which is what it matters, is what is the market on this. So it takes about 200 days for this crop to be harvested. Just recently, with my collaborators, Daniel and Roberto, we published this literature review about nitrogen management in onions. And Daniel put together a couple of papers, about the nitrogen in above ground biomass and the timing, of how this happens, and as I showed previously, pretty much, 50% of the time, the first 150 days, pretty much nothing happens, with these onions in terms of nitrogen uptake, it's really a really small amount of nitrogen taken by the plants, but then it's so exponentially that, the last part of the season, the last two months, it takes most of the nitrogen, to grow the bulbs. So at the end of harvest, what we notice, in our review is the nitrogen happens pretty much in the bulb, 65% versus 35% of the nitrogen in the leaves. So that's pretty much the partition at harvesting. So the goal of this project is to pretty much to evaluate the water regimes and nitrogen rates in onion production here in Imperial County. What we have been doing, for the last 2 seasons, from 2019 to last year, was to have the irrigation treatments, is the main plot, we have 4 crop evapotranspiration rates from 40 to 130%. And then we have in that main plot, we have 4 subplots with nitrogen. And one of them, we only use pre-plant if we use any pre-plant there, or we added 75 pounds to all the way to 225 pounds. Here in the valley, usually the growers use about 50 pounds of nitrogen for pre-plant, and then about 240 pounds per acre during the season. So our treatment, the highest nitrogen treatment is pretty much the standard, in our here with our growers. Irrigation scheduling, it was a water balance. We use our Siemens weather station here at the station, and also we use crop coefficients developed locally by our advisor, Ali Montasar. We use 40-inch beds, 4 lines of onions, as you can see in this picture on the left. The kind of soil that we have at the center is pretty much clay soil, on the top 1 foot. We use sprinklers for germination for establishment as kind of the usual practice here in the valley. And then we transition to drip, from bulb initiation to harvest. During the season, we fertilize the plots 3 times. Next week, I'm going to do the fertilization for this year. So it's going to take about a month. So we split the fertilization in 3 irrigations during the season. So pretty much in February that happens. And this graph can show you, the kind of weather we have here in the Imperial Valley, from October all the way to the harvesting. So we can see the maximum and minimum temperatures. And we see, right now we are getting into the lowers. This picture is from their data from 2019 to 2020 season. So we can see that we have a pretty much a mild winter, but still, it's kind of dormant, those plants, and nothing much happens here. In this particular year, we got a lot of rain. We say, how much is a lot? We have 4 inches of rain. And as you can see here, early March, on 2020, we got more than 1 inch, rain, that happened, so that was pretty much unusual, but it happens, here sometimes. But then, the temperature start rising, and the transpiration and evaporation, rise as well. So, and the crops start, developing faster. So that's pretty much, our weather pattern here in the valley for the onion season. So this picture shows you how we deal with the irrigation treatments. So as I said before, we use sprinkler irrigation from germination all the way to establishment. So it takes a lot of time, as you can see in this. But then after that, we transition to our drip irrigation and our irrigation treatments. So you can see that we follow a pretty strict schedule on these ones. And this drip irrigations happens every other week, usually most of the time, but at the end, maybe happens on a weekly basis, depending on the water needs of the crop. You can see also how the difference, at the end, from the total amount of water, goes from 16 inches all the way to 26 inches for this particular year that was this past year. So we really did good management, of water in this plot, according to the criteria. We deployed an army of soil moisture sensors and soil water retention sensors as well, on these plots. And we put together these graphs, the soil water retention curves, where we show, the volumetric water content percentage versus soil water retention. So these plots is for the 130% ETC. You can see in this picture that the beds were really overweighted, every time that we put water on these fields, and see that pretty much all the lecture, readings at 6 and 12 inches happens, in this range, between field capacity and permanent wilting points. So there was no stress at all, in these fields. But as we progress, as we reduce the amount of water, we are seeing that these graphs, especially the 6 inches readings, are moving towards below permanent wilting point. But still, the 12 inches is still, in the wood available. And the tension, is also, it's also moving. So it's going to be harder for the plants to start taking water. When we move to 70% ETC, the graph, pretty much the 6 inches, most of the data, this is hourly readings that we collect in those fields. Pretty much the 6 inches, was pretty much dry out, but the 12 inches readings, the yellow ones, is still, with some amount of water there. But if we move all the way to 40%, we see, this shift all the way to high tension, to the right, and no available water, below the permanent wetting point. So we can see that the plants didn't have the available water or easy water, for crop production at 40% ETC. So let me show you a couple of results. Let's gonna start with the irrigation effects. This graph comes from the first year, 2019 to 2020. We can see that we have great yields. The expectation from the growers on fresh market onions is about 45 tons per acre on 4-inch beds. That's what they are expecting, and we got with this variety that was Terrena at that time. We got 50 inches. What we can see here too is also a nice curve, that the more water we add, the higher the yield. And also the other important factor is larger sizes as well. The larger the size, the better the price, for those ones. So really a nice, graph, showing the effects of water. And also we keep one treatment that we call Drought. In this Drought treatment, basically we just we cut water after establishment, so we didn't put any drip irrigation water on this. So we can see, the big effects, of water, especially during the faster growing season, the last 2 or 3 months, and what happens, with your crop if you don't irrigate accordingly. Also in this one, we can see that in this season we receive about 5 inches of rain, and so that was pretty unique, for that year. The next year we receive less than that. But at the end, we can see that between 20 to 24 inches of water, that was good enough, to have a high production onion in large sizes here in our experiment. For the next year, the 2020, 2021, we pretty much follow the same trend, on the water effects on the yields, along with also the effects on the sizes. This graph, show you that most of the data, goes, especially on these 2 treatments, the 100% and 130%. Most of the production goes into the jumbo size. That's that's the target. That's most of the target here for the growers for fresh market onions, the jumbos, along with the colossals and super colossals. For this season, we use a different variety. It's a yellow type 2, but it's a hornet variety that show you good results. But still, our yields were lower than the previous year by a lot, about 15 tons per acre less than the other one. For this particular year, our yield, our plant density was lower as well. So that was one factor, on this one. That also we have lesser production as well. Okay, let's gonna see what was the impact, on our nitrogen treatments. Remember that nitrogen treatment 1 means that only was pre-plant, if happens, on that time, all the way to 75, 150, and 225 pounds per acre during the season. So we can see here there was no significant difference, on our yields, neither on our sizes. So there was no impact, on these 2 categories in terms of nitrogen impact on yields and sizes. So what we did was, let me break down, what happened during that season. We have initial residual soil mineral nitrogen in the top 1 foot, 70 pounds per acre. And then we apply pretty much the standard that the growers applied, about 56 pounds per acre, pre-plant. And then during the season, we have the, the nitrogen treatment, the 0 to 225. And the total fertilizer applied was here. And at the end, the total available mineral nitrogen range, from 100 to 350 pounds per acre. So the range is huge, but we didn't see the impact, on our yields and neither our sizes. What happened the year after or last year? Okay, the previous year our rotation was from a vegetable crop. So on this year, the 2021, our rotation came out of an alfalfa field. So we can see the initial residual was higher, and again, we didn't find out any significant difference, among our treatments, neither on yields and neither on the sizes of these onions. But we got more initial residual than the previous year. The previous year was around 70 pounds per acre. This year was 100. So that makes sense, because we were coming out of this alfalfa field. In that part, we figured that we are not going to apply any pre-plant because we have enough, from the residual soil mineral nitrogen, and we did our normal in-season fertilizer management. At the end, the range, was pretty much similar to the previous year. The total available mineral nitrogen was from 100 to 300 pounds. That's a huge range, but again, we didn't find out, any insights, or differences in the years, neither on the sizes. Okay, let's gonna move on and check, in general our nitrogen balance. I'm just gonna give you, a summary, what we find out, during these years, especially during this season, the 2021. In terms of nitrogen inputs, we range, from 0 to 225 pounds per acre that we apply to the crop, but the initial residual nitrogen was close to 250 pounds per acre on the top 3 foot of the soil. So when the babies came out, we measured that the crop took anywhere from 170 to 250 pounds per acre of nitrogen. That's the uptake from the crop. But also the final residual from this season was anywhere from 100 to 500 pounds per acre on the top 3 foot profile. So what is the balance? The balance is a positive, anywhere from 40 to 100. We are just mixing, all the treatments here. So just to give you a flavor, of what's going on with the nitrogen balance. So our in general balances were positive. This means that we are missing some input. One of these missing inputs is the nitrogen mineralization, and our best estimates, after going through discussions in the group and reviewing the literature and doing some preliminary analysis, we figured that nitrogen mineralization could be in the order of 100 pounds per acre, that may happen during the growing season. So that's pretty much that give you, an idea of what's going on there. So we can see that because these are rotational fields, there is a lot of nitrogen residual, and at the end, the crop can leave, a lot of nitrogen as well. So nitrogen mineralization is key, in order to better management this crop, in terms of nitrogen, and as well, having data as a pre-plan in order to do a better management approach to nitrogen. So let's gonna see what's going on with the post-harvest analysis. We check on 2 characteristics on these onions: the fairness in pounds and the bricks. That's the total soluble solids in the onion. So we have here that pretty much nothing happened. We didn't find out any statistical difference, with irrigation rates, affecting those 2 parameters. But the nitrogen for this trial, the first year with the terrain variety, we see effects, on the bricks. So we are seeing the effects, on this one. So we are seeing that the more nitrogen that we apply, the less sweeter were these onions. This post-harvest analysis was done only on jumbo sizes, just to clarify to you. So this is what we find out. So the effects only on nitrogen on the bricks on the first year. On the second year, the bricks was also affected, but in this case was on the irrigation. So the irrigation, affects, the bricks, but the nitrogen did not affect the bricks. The other thing that we find out in this one is the biority, the hornet. At this time, it was harder than the previous biority, the Terrena. So this show you a couple of pictures how we check on the furnace and also the bricks.
1 minute, Jairo.
All right. So this is the last one. The last minute, the take-home message is that the irrigation affects considerably the quality and quantity, of the onion here in Imperial County. We need to dig more in deep, and have a better understanding of nitrogen fertilization of onions. And there is a lot of nitrogen residual. So there is a lot of gaps, that we have to fill in the coming years, but there is plenty of opportunities to improve nitrogen management here in the valley, and also do a better management of water as well, in order to have a better efficiencies all around. I wanted to acknowledge the funding agencies, CDFA, all the amazing work that we have, labor and staff, at Desert Rec, all the students that have been, working also in getting training under my supervision here at Desert Rec, and also the growers, that is the inspiration, and also the great collaboration we have with them, in order to learn, in order to exchange information along with the Toro company who has been donating the drip tape these 2 years. And that's my contact information. And we have any questions?
Please leave your contact information up. Jairo, thank you very much for your presentation. Shared wonderful information with some nice up-to-date research. I don't think we have time for answering questions live right now, but you do have a question in the Q&A function. And as a reminder, anybody who has questions for Jairo, please throw your questions into the Q&A function. I'd like to thank all of our speakers in the nutrient management session. And of course, thank you to my co-chair of this session, Daniel Geisler, and all of the attendees of this session, and to the sponsors of this meeting. And now I'll pass the mic over to Florence Castle.
Thank you, Nick. Thank you very much for this very interesting session. So this actually concludes our 2022 Plant and Soil Conference. So on behalf of the chapter and the organizing committee, I would like to thank all the speakers for contributing to our sessions over the past 3 days. We really had a good program. So thank you for your time in putting together your presentation and answering all the questions. And also, we appreciate everybody in attendance. Thank you for those of you who was sticking around until the last presentation. That's really good. So we hope that we were able to bring you some good content this year, able to share some new research, new technology, and hopefully generate some interesting kind of thought. And we had a few discussions, and hopefully we can inspire, like, let's say, maybe a new question, new research that we can carry on over the next few months, and maybe address some of those at our next conference. So we would like to hear your feedback, as usual. And I think Clint posted the link for the evaluation. So please look at the link. I think we are going to post it after we just end our remarks. But it's very important for us as we prepare for the next conference. So again, thank you for all the sponsors who were very generous, helping us with the award and the conference in general. And so we hope to see you next year. And with that, I'll pass it along to Michelle.
I don't have anything more to add except see you next year, everybody. Thanks for your participation.